Imagine standing at the edge of the ocean at dusk. The last glow of the sun has slipped beneath the horizon. You watch the waves erase your footprints. From here to the horizon is about 5 kilometers, far enough that you cannot read the expression on a stranger's face, but still, a distance your own feet could carry you before midnight. Now lift your gaze. Above the dark water, the first star appears, steady and silent. That point of light left its surface hundreds of years ago. It traveled across a blackness so absolute that no day or night exists within it. It outlived every kingdom that ever raised a flag. It arrived just in time to meet your eye. The span between that star and you is what we call a light year, and it is the measure that finally breaks the comforting scale of continents and lifetimes. For most of human history, we did not need such a measure. Babylonian scholars counted the heavens as a dome overhead, a ceiling painted upon which the planets wandered. Greek astronomers placed the fixed stars upon a crystal sphere that turned once each day. Even then, curiosity pressed further. Aristarchus of Samos guessed that Earth circles the sun, and if so, the stars must be immeasurably distant. Otherwise, they would betray the motion by shifting their places. He had no instrument fine enough to prove the idea, yet the question lingered: how far is far? When Kepler refined the orbits of the planets, the solar system shrank to a clockwork model you could hold in your mind. A few decades later, Giovanni Cassini measured the distance to Mars by watching it from Paris while a colleague watched from French Guiana. The angle between their two lines of sight, only a whisper of degrees, yielded the first credible span to another world. It was a triumph of ingenuity, yet even that distance, tens of millions of kilometers, was already beyond the vocabulary of ordinary life. No road sign counts in millions. No heartbeat lasts long enough to pace such a journey. Still, astronomers pressed outward, driven by a simple, stubborn need to know. By the 19th century, the parallax of nearby stars revealed that the closest neighbors of the Sun float more than 40 trillion kilometers away. Write that number out, a 4 followed by 13 zeros. Speak it aloud and it dissolves into abstraction. We are left holding a yardstick that once reached from kitchen to garden gate, now asked to span oceans of emptiness larger than Earth itself. Miles and kilometers buckle under the burden. They were invented for property deeds and railway timetables, not for mapping the galaxy. A new unit was required, one stitched not to the human stride but to the universe's own speed limit, the distance light travels in a single Earth year. The light year was born quietly in the journals of the 1830s, first as a convenience, then as a revelation. It is not, as newcomers suppose, a measure of time but of distance. Light slips through space at 299,792 kilometers each second. Let it roam for a year, and it lays down a trail nearly 10 trillion kilometers long. That number is still too vast for the mind to grip, so borrow another image. If the sun were shrunk to the size of a blood cell, the solar system would fit inside a dinner plate. On that scale, the nearest star is a second blood cell 200 kilometers away, and the light year becomes the thickness of a single human hair laid across that gulf. The galaxy, then, is a continent of such hairs, overlapping until they weave a fabric of stars. Yet even this unit is modest. The star you noticed over the ocean may be hundreds of light years away. The familiar constellations are scattered across thousands. The Milky Way itself spans 100,000 of these threads of light. And beyond our galaxy lie island universes, other Milky Ways, each separated by millions of light years, each carrying its own cargo of billions of stars, perhaps billions of planets, perhaps moments when other eyes look up and wonder. We do not journey to such places. We do not pack provisions or chart coastlines. We receive their ancient postcards, photons that departed when our kind still hunted mammoths with stone. The distance is not merely spatial. It is temporal, To look outward is to look backward. Every glance at the night sky is an act of archaeology. What does this do to the heart? On clear evenings, the enormity can feel like a weight pressing the sternum. Yet there is a counterbalance. The same scale that isolates us also connects us. The calcium in your bones was forged in stars that blew apart before Earth existed. The iron that colors your blood red was launched across light years of vacuum to arrive here, to season the crust, to enter the food chain to become you. We are not separate from the cosmos. We are its offspring, thinking about its own depths with nerves built from stardust. The light year, then, is not an alien unit. It is the family photograph that finally shows where we come from. Still, a mystery remains wrapped inside every measurement. Why does light take time at all? Why is the speed finite rather than instantaneous? No law of physics demands that the universe be constructed so that we can see the past. Yet here we are, granted a view that stretches 13 billion light years in every direction, a horizon set by the birth of light itself. We do not know whether space continues beyond that horizon, or whether other universes float beyond the reach of any possible signal. The light year gives us a language for what we can see, and in doing so, it sketches the boundary of what we cannot. So stand again at the shoreline. The stars tremble overhead like reflections on black water. Each gleam is a messenger, a courier carrying news from epochs when the continents lay elsewhere and the seas were different. The distance that breaks our brains is also the distance that tells our story. And tonight, the story is only beginning. Imagine you are standing on a quiet shoreline at dusk. A lighthouse on the far horizon begins to flash. The beam leaves the lamp, skims the waves, and reaches your eyes only after the briefest pause, so brief it feels instantaneous. Yet that pause is real. Light, racing at its ancient speed, needed time to cross the water. If the lighthouse were farther, the pause would lengthen. If it were on the moon, the delay would outlast a heartbeat. If it stood on the sun, the hush would last 8 full minutes. Each second of waiting is not a quirk of the lamp. It is the geometry of space itself, measured by light's unhurried travel. Now, let the shore dissolve. Let Earth shrink to a speck, then to nothing. Let the lighthouse become a star, then a galaxy. The same rule governs. Light never hurries. It crosses the black gulf at 300,000 kilometers each second, swift beyond any earthly stride, yet obedient to a single, unbreakable pace. Because that pace is fixed, distance and time become two faces of the same coin. To say a star is 20 light years away is to say its glow has spent 20 years on the road, riding the only highway the cosmos provides. Picture a year of light's travel. Not a second, not a minute, a year. A year is long enough to hold seasons, birthdays, the slow drift of constellations. A year of light is a ribbon of motion almost 10 trillion kilometers long. No human mind can compass such a span directly. We translate it into something we can feel. 10 trillion kilometers is the distance our planet would cover in 7,000 centuries of orbiting the sun. Yet light covers it in one quiet year, gliding through vacuum, asking no permission, leaving no footprint. This is why astronomers speak of light years instead of kilometers or miles. Kilometers are for roads. Light years are for memory. They tell us not how far away a star is in space, but how far it is in time. When we look at Sirius, we do not see the brilliant beacon that hangs tonight above the skyline. We see the beacon that began its journey 9 years ago, perhaps while you were learning to walk, perhaps while a forest was still a sapling. The light arrives intact, carrying the stamp of its departure. The star may have changed in the interval. We will not know until another 9-year parcel reaches us. There is a subtlety here. A light year is not a measure of time, though it sounds like one. It is a measure of distance, expressed in the currency of time. It is the distance light can travel in one earthly year, no more, no less. The distinction matters. If you could hitch a ride on a photon, you would cross 1 light-year of space in 1 year of our clocks. But you would experience no year at all. Within the frame of light itself, duration collapses. Departure and arrival share the same instant. Only those who remain behind, stationary on planets, drifting in spacecraft, feel the interval. Thus, a light year is a gift granted to the watchers, not to the travelers. This gift gives us a ruler longer than any tape. The nearest star, Proxima Centauri, lies 4¼ light years away. Its photons depart the star's crimson surface, slip through the void, and tap our detectors after a journey longer than most governments endure. Extend the gaze. The center of our galaxy lies 26,000 light-years away. The light we collect tonight began when humans first planted seeds in the soil, when mammoths still walked. Look farther. The Andromeda Galaxy hovers 2.5 million light-years distant. Its glow left before our species existed, before the first stone tools, before the Himalayas had fully risen. Each photon is a postcard mailed from a world we will never touch, postmarked by time itself. Notice how this changes the night sky. Every bright spot is a clock face. The number it shows is not the hour, but the epoch. Orion's shoulder betrays 600 years. The Pleiades whisper 400. The farthest galaxies captured by long exposures disclose themselves as they were when the universe was young, their light strained and reddened by expansion, their shapes belonging to an era when the sun had not yet formed. We stand at the center of a cosmic onion, each layer older than the last, each peel revealing a deeper past. There is comfort in this constancy. Light never lies about its age. It carries in its color and brightness the conditions of its birth. Analyze the spectrum and you read the temperature, the chemistry, the motion of the place where the journey began. The star may have died, but its last testament travels on, honest and unaltered, a messenger that can be cross-examined centuries later. In this way, light is both witness and archive. It preserves what the cosmos would otherwise forget. Yet the same constancy imposes a strange loneliness. No signal can outrun light. If a star erupts in supernova tonight, we cannot be warned in advance. The flash and the news arrive together. Likewise, any reply we might send to a distant civilization would require the same span of years to return. Conversation across the galaxy becomes a correspondence of centuries, each letter delivered by a courier that never accelerates. The speed of light binds us to a temporal diaspora. Every part of the universe sees every other part only as it once was, never as it is. Still, we make peace with the lag. We build our science upon it. Maps of the Milky Way are maps of memory. Charts of galaxy clusters are family albums of earlier eras. By comparing nearer galaxies with farther ones, we watch the universe grow up. We see that star birth was more vigorous in the past, that collisions were more common, that dark matter already held sway before light had time to cross the infant void. The finite speed of light, once a hindrance, becomes a time machine provided gratis to any creature with a lens and patience. Consider the practicality. To express cosmic distance in kilometers would bury us in zeros. To express it in light travel time is to tell a story. A child can grasp that the moon's light is 1 second old. The same child, grown older, can feel the weight of knowing that the nearest galaxy beyond our own is 2 million year light. The unit scales with the mind. It carries emotion as well as magnitude. It reminds us that looking outward is looking backward, that every gaze into the sky is an act of archaeology. And so we drift beneath the great lantern, collecting photons that departed before our troubles began, before our nations were named, before the atoms of our bodies were forged. Each shard of light is a thread, stitching us to the vast, slow weaving of space and time. Pull gently on the thread and the fabric responds, not with sound, but with silence. A silence that has traveled far and that will travel farther still, long after the last eyes close. Somewhere ahead, beyond the next chapter of distance, the light that left today is already on its way. It carries our moment, our colors, our brief flicker of thought. It races outward, unwearied, unbending, destined to arrive in a future we will not share. What stories it may tell then, we can only imagine. For now, we keep watch, measuring the heavens not with strings but with years, years of light, years of memory, years that stretch like calm water toward an ever-receding horizon. Sunlight warms your eyelids in the morning. Starlight slips into your pupils at night. Both arrive as silent, weightless messengers, yet they announce two very different neighborhoods, one close enough to touch, the other so remote that distance itself becomes a form of strangeness. To walk from the first neighborhood to the second, we must begin with the simplest stride, the gap between Earth and its parent star. Astronomers call that span an astronomical unit, a phrase that sounds official until you whisper the numbers: 149 million kilometers. If you drove a fast car straight up at highway speed, you would reach the sun in 170 years, assuming the engine never cooled and the road never bent. Light makes the same journey in 8 minutes and 19 seconds. 8 minutes is the time it takes to rinse a plate of dinner or to hum the length of a lullaby. 8 minutes is also the definition of a border, anything inside that radius shares the same moment of now with Earth. Anything farther speaks to us from the past. Fold 8 minutes into a whole year, and you have the astronomical unit stretched into a ribbon 6 trillion kilometers long. That ribbon is a light year, not a span of time but a distance measured by the patience of light. Hold the ribbon's end at the sun and let it unroll through emptiness. When it completes one full revolution around the calendar, the place where the ribbon rests is 1 year older in our sky, though the light itself has aged not at all. With that ribbon, we can begin to survey the immediate family of the sun. The moon, our silver companion, lies less than 2 light seconds away. Apollo crews crossed the gap in 3 days, trusting chemical fire and calculus. 3 days feels trivial when compared to the 8-minute light dash to the sun, yet both distances fit comfortably inside the parentheses of earthly intuition. We have hurled machines to the moon, to Mars, even to the chilly outskirts where Pluto wanders. Every milestone so far remains within the sun's light tower, a province so small that a single heartbeat on a quiet night outlasts the photon's commute across it. But beyond that province, the suburbs of the galaxy begin and our intuition starts to falter. To step farther, we must learn a new trick of vision. Hold a finger before your eyes. Close the left, then the right. The finger jumps against the distant wall. That jump is parallax, the apparent shift caused by a change in vantage point. Your brain measures the shift instinctively and estimates the finger's distance. Astronomers perform the same childhood maneuver on the cosmos, except the eyes are 2 positions of Earth on opposite sides of the sun, 6 months and 300 million kilometers apart. Instead of a finger, they watch a nearby star. Instead of a wall, they use the remote stellar backdrop. The star jumps a tiny angle, less than the width of a coin seen from the far end of a soccer pitch, yet that angle, once measured, yields distance. The first successful measurement was accomplished in 1838 by Friedrich Bessel, who selected a faint star in the constellation Cygnus because it showed the largest known proper motion, a clue that it might be close. His result placed the star at a distance of 10 light years, an announcement that stunned a public accustomed to thinking of the heavens as a dome of lamps. Suddenly, the universe had depth, and depth implied history. Parallax works beautifully for the nearest 1,000 stars, a modest census that extends out to roughly 500 light years. Beyond that, the jump becomes too small to register from Earth's orbit alone. To measure farther, we must widen the baseline or find brighter yardsticks or both. Yet within the parallax frontier lies a jewel, Proxima Centauri, the nearest star that is not our sun. It glows red, dim enough to be invisible to the unaided eye, yet it grazes our threshold of presence at 4.24 light-years. Imagine a lighthouse whose beam must travel across a dark sea for 4 years and 3 months before it brushes your retina. The photons that reach you tonight left the lighthouse when screens were smaller, cities quieter, and you were a slightly different person. Proxima is not alone. It belongs to a trio of suns that orbit one another in slow gravitational choreography. Alpha Centauri A and B, the brighter pair, whirl around a common center every 80 years, while Proxima traces a wider, more leisurely circuit, bound by gravity but separated by thousands of astronomical units. From a planet orbiting Proxima, our sun would appear as a solitary yellow star in the constellation Cassiopeia, bright enough to cast shadows on an airless moon, yet still remote enough to require a telescope to resolve its attendant planets. Early astronomers did not have such telescopes, nor did they possess precise clocks or photographic plates. They relied on the unaided eye, on memory, on the assumption that the heavens were immutable. When Tycho Brahe noticed in 1572 that a new star had appeared in Cassiopeia, he shattered the dogma of changeless skies, but he still lacked the tools to gauge its distance. He could only say that the newcomer lay beyond the moon because it showed no measurable parallax against the lunar disk. That was a revolutionary admission. The universe was larger than the orbit of the moon, perhaps infinitely so. Yet infinity is a destination impossible to reach by walking halfway, and the absence of parallax could mean either vast distance or celestial perfection. The paradox lingered for 2 centuries, until improved instruments and patient record-keeping allowed Bessel's triumph. Even then, the measured distances were so vast that many Victorian thinkers recoiled from their implications. If light took years to reach us, the stars might have burned out already, their death notices still en route. The cosmos became a gallery of ghosts, each shining in our sky long after its own present had moved on. Today, we measure stellar distances with laser beams bounced off satellites, with interferometers whose mirrors ride on rails smoother than a strand of spider silk, with spacecraft that gaze from the void beyond Saturn. The European Space Agency's Gaia satellite has mapped more than 1 billion stars, recording their parallaxes to the width of a human hair seen from 1,000 kilometers. Yet the principle remains what it was when shepherd astronomers traced constellations in Babylonian dusk. Shift your stance, watch the sky pivot, read depth in the angle of that pivot. The difference is only in the fineness of the stance and the clarity of the watching. In that clarity, we have learned that distance is not merely emptiness but a container of time. Every kilometer is a micro-archive of the past, and a light year is a full archive, neatly labeled with the year of departure. Consider, then, the conversation we are having with Proxima Centauri. The star itself may host planets, perhaps even a rocky world warmed enough to harbor liquid water under a flaring red sun. If inhabitants of that world pointed a telescope toward Earth 4 years ago, they would see our planet as it was in the season you lived through recently. They would see the light reflected from oceans and continents, the night side dotted with the faint sodium glow of our cities. They would not yet know what you had for breakfast this morning. That memo will not reach them until the spring of 2028. We are forever slightly out of sync, pen pals whose envelopes travel at the speed of light across a gulf too wide for casual remarks. Multiply that gulf by the 100 billion stars in the Milky Way, and you sense the quiet immensity within which our dramas unfold. Still, the immensity is not hostile, it is simply indifferent. The light year, that impossible ribbon, becomes a kind of mercy. It shrinks the galaxy to a map we can fold in the mind, a chart where destinations are labeled not in kilometers but in years of travel at nature's fastest pace. On such a map, Proxima is 4 steps away, Sirius 8, Vega 25. The center of the galaxy is 26,000 steps, a pilgrimage beyond recorded history. Andromeda, our nearest spiral neighbor, is 2 million steps, a journey older than the genus Homo. Each step is a year of darkness threaded by a single beam that left its source before the question of arrival could even be asked. We began with sunlight on closed eyelids, continued to moonlight on cratered plains, and ended with starlight that outlives the seasons that witnessed its departure. Somewhere between the 8-minute commute of a photon and the 4-year voyage from Proxima lies the boundary where Earth-scale intuition dissolves into interstellar-scale humility. Crossing that boundary, we leave behind the certainty of mileage signs and enter the realm of time itself as the only ruler. Yet even time bends under the weight of distance. Simultaneity becomes a local custom, and the present moment fragments into a scatter of nows, each valid for a different observer moving through the dark. As we stand at this shoreline, a question drifts like smoke. If every distance is also a delay, how do we ever truly meet the universe rather than its echo? Perhaps we do not. Perhaps to meet the cosmos is to accept that we are always listening to an aftermath, and that the only complete conversation is the one we conduct with the light still en route, the messages we encode in new beams cast back across the same gulf that brings starlight to our eyes. The next chapter will follow one such message, a human-made whisper launched 4 decades ago, riding on a craft of aluminum and golden foil, outward bound toward the stars we have just learned to measure. Out there, distance will grow stranger still, and the meaning of a light year will stretch until it snaps into something we do not yet have a name for. But that is another journey, another darkness, another story waiting in the cold between the stars. Imagine standing on a beach at night, eyes closed, arms outstretched. You turn your head the tiniest fraction, and the sound of the surf seems to shift inside your skull. That microscopic tilt is enough to change the way the ocean's voice reaches each ear. Now, instead of your head, let the Earth itself pivot by the width of its orbit. Instead of surf, let the stars be the source. Instead of sound, let light be the messenger. Open your eyes, and you will see the nearer constellations slide against the farther ones, as if the sky were a slow, layered theater curtain. That sliding is parallax, the first rung of the ladder we must climb if we ever hope to measure the cosmos without going mad. Hold out your hand at arm's length. Close one eye, then the other. Your thumb jumps against the distant background. The jump is tiny, yet you can feel it. Shrink that jump to the width of a telescope's pixel, stretch the baseline to 300 million kilometers, Earth on one side of the Sun, then 6 months later on the opposite side. And the jump of a nearby star becomes a tremor 1,000 times smaller than the width of a human hair held at arm's length. Astronomers call it the parallax angle, and from it they coax distance with a certainty that would make surveyors weep. Within a few hundred light years, this method is sovereign. Beyond, the tremor is too slight, the hair too fine, and the ladder must reach higher. So we look for stars that breathe, not the slow stellar wind of aging suns, but a real, rhythmic swelling and shrinking like lungs made of plasma. Cepheid variables brighten and fade over days or weeks, and the slower the breath, the larger the lantern. Henrietta Swan Leavitt discovered this secret in 1908 while cataloging plates under the hum of electric lights in Cambridge, Massachusetts. She found that the period of the pulse predicted the true wattage of the bulb. Compare the wattage you know with the wattage you see, and you can judge how far the light has traveled. A Cepheid shining 100,000 times brighter than our sun can be seen in galaxies tens of millions of light years away. Each new detection is another candle set upon the cosmic mantelpiece, flickering its invitation across the dark. Yet candles, however faithful, gutter. Beyond 100 million light-years, their light is too faint for even the largest mirrors to capture the pulse. We need lanterns that detonate. White dwarfs, the spent embers of sun-like stars, sometimes sip fresh hydrogen from a companion. The stolen gas piles up until a thermonuclear flash ignites the dwarf's entire surface, ripping it apart in a blaze that can outshine a galaxy for weeks. These are Type Ia supernovae, and they all ignite at nearly the same mass, therefore nearly the same brightness. Spot 1, wait for its peak, measure how dim it appears, and you have a standard candle visible halfway across the observable universe. Each such explosion is a graveyard and a beacon in one, announcing both death and distance with exquisite honesty. Still, supernovae are rare. A galaxy the size of our Milky Way hosts one perhaps every 4 centuries. To chart the quieter expanses, astronomers listen for the whispered spins of spiral galaxies. Stars in these whirlpools orbit at speeds set by the mass they enclose. The faster the spin, the brighter the galaxy, a relation first noticed by R. Brent Tully and J. Richard Fisher in 1977. Measure the width of a hydrogen line broadened by galactic rotation, and you infer the galaxy's true luminosity. Compare that to the feeble glow you receive, and another rung appears. This rung is less certain than supernovae, more certain than foggy guesses, and it stitches together clusters of galaxies like stepping stones across a dark river. Beyond a few billion light-years, the canvas itself begins to ripple. Space expands, stretching the very wavelength of light that travels through it. A photon leaves a distant galaxy in the ultraviolet, and by the time it reaches Earth, it has been pulled so thin it arrives as infrared. Redshift, the name for this stretching, becomes a proxy for distance. At first, the relation is linear: double the redshift, double the distance. But as we peer further, the expansion history of the universe bends the ladder into a curve. To climb safely, we must know how quickly the cosmos has breathed across the eons. We must weigh dark matter, taste dark energy, account for the way galaxies cluster like foam on the surface of an ever-widening tide. Each correction is a murmur of uncertainty, a reminder that our instruments are also embedded in the very fabric they attempt to measure. Every rung inherits the errors of the one below. Parallax can misjudge a star's motion through the galaxy. Cepheids may be dimmed by interstellar dust. Supernovae could vary slightly in their intrinsic brightness. Tully-Fisher calibrations depend on how cleanly a galaxy's edge is seen. Redshift mingles distance with the universe's own evolution. Astronomers speak of error bars the way sailors speak of squalls. With respect, never certainty. Yet the miracle is that the bars shrink as methods overlap. Where parallax and Cepheids both reach, agreement tightens. Where Cepheids and supernovae coexist, the candle's flame steadies. Layer upon layer, the latter becomes less a fragile thing and more a braid, many strands twisting into strength. Stand at the top and look back. The Earth is a moat beneath your feet, the sun a spark you could hide behind a fingernail at arm's length. The nearest star is a doorstep 4 light-years away. The width of our galaxy, 100,000 light-years, is a slow afternoon stroll compared to the gulf between us and the Virgo cluster, 60 million light-years off. Press your eye to the deepest fields, where redshift exceeds 7, and you are witnessing a universe younger than its own stars now appear. The light left those galaxies when the cosmos was a toddler, yet it has traveled for over 13 billion years to arrive as a single silver grain on a detector colder than winter on Pluto. Each photon is a postcard written in a language older than Earth itself. We do not see these distances. We infer them, one inference balanced upon another, like ancient astronomers who once balanced crystal spheres. The difference is that our spheres are tested by starlight, not dogma. Still, the vertigo is the same. To speak of a galaxy at redshift 8 is to speak of something so remote that the expansion of space between us carries it away faster than light itself. It is not that the galaxy races through space, but that space itself widens like raisins in rising dough, each raisin standing still yet growing ever farther from its neighbors. The latter does not merely measure. It reveals the dough expanding, the oven of time itself set to a temperature we are only beginning to sense. There are places the latter cannot yet reach. The first black hole mergers detected in gravitational waves carry distance information encoded in the tremor of spacetime, but we are still learning how to calibrate that new kind of tape. The cosmic microwave background, a wall of light released when the universe became transparent, lies at a fixed redshift of 1,000. Yet its tiny fluctuations whisper of dark energy and curvature. We stitch these whispers into the braid, hoping they will one day let us step beyond the last visible galaxy. Perhaps we will find that the expansion rate we measure nearby drifts from the rate inferred from the early universe, a tension that may hint undiscovered physics or merely undiscovered dust. For now, we live in the age of overlap. The European Space Agency's Gaia satellite pins parallaxes with microarcsecond grace. The James Webb Space Telescope watches Cepheids in galaxies that once hosted supernovae, tightening the calibration. The Vera Rubin Observatory, under construction on a Chilean ridge, will inventory billions of galaxies, catching thousands of new supernovae, mapping the cosmic braid in finer thread. Each observation is a quiet act of faith, that the universe is not capricious, that candles burn the same here as in the distant past, that the laws which govern the hydrogen atom in the laboratory also govern the hydrogen whispering from the edge of time. And so we climb, not because the distances are comfortable, but because they are true. We climb to know how small we are and how briefly we burn. We climb to place our moment, our loves, our wars, our brief dawn, against the long curve of cosmic becoming. The latter does not promise safety. It promises only that if we measure carefully, the universe will answer with silence or with starlight, and sometimes both at once. One day the last rung may dissolve into quantum foam or into a darkness deeper than any we have named. Until then, we steady our hands on the parallax of a star, the pulse of a Cepheid, the flare of a supernova, the spin of a galaxy, the redshift of ancient light. We place our weight upon them and we look up and we go on. Imagine climbing behind the wheel of an ordinary car, pointing it skyward, and pressing the accelerator until the speedometer locks at a steady 100 kilometers per hour. You would leave the driveway, rise through the clouds, and cruise through the thinning blue. If gravity kindly stepped aside and the road remained miraculously straight, you would reach the moon in roughly 4 months of unbroken driving. 120 sunrise-to-sunrise cycles of steady motion, headlights cutting across lunar craters that have waited 4 billion years for your arrival. 4 months feels manageable. We have all endured seasons that seemed longer. Yet that same steady pace, continued without pause, would carry you to the sun in a little more than a century. A newborn could start the journey, and a great-grandchild could roll to a stop beside the photosphere just in time to watch the last embers of the family story fade into solar fire. Extend the same road to the nearest star, Proxima Centauri, and the drive becomes something else entirely. At 100 kilometers per hour, the same calm speed that carried you to the moon in a season, you would now have to keep driving for 40 million years. 40 million quiet dawns, 40 million tanks of fuel, 40 million winters that still would not bring you even halfway. The mind recoils, not because the numbers are large, but because they are large in human time. We can feel a season, remember a century, gesture toward a millennium. Yet beyond a certain horizon our memories run out and imagination must take the wheel. So let us leave the car behind and try something slower, something our bodies already know. Imagine you could walk to Proxima Centauri at a gentle strolling pace, one foot after another, mile after mile, across the invisible bridge of space. If you set out today, you would arrive in roughly 300 million years. Dinosaurs would rise and fall behind you, continents would drift like rafts. The familiar patterns of stars overhead would shuffle into new constellations while you, patient walker, continued your solitary commute. By the time your foot finally touched the soil of a planet circling another sun, the Earth you remembered would be unrecognizable, perhaps unrecognizing. These comparisons are sobering, yet they only carry us to the edge of the cosmic neighborhood. To reach the center of our galaxy on foot would require a hike lasting 100 billion years, a duration older than the universe itself. At that point, walking becomes meaningless, the body becomes meaningless. The comparison collapses under its own weight. Still, we try because the alternative is to accept that our senses are simply not calibrated for the scale on which the universe actually operates. Another way to picture distance is to stack the things we know best. Begin with Earth itself. Lay the planet's 8,000 miles of diameter end to end and watch the pile grow. Stack two Earths 10, 100, 1,000. A tower of 10,000 Earths would barely reach the moon. Stack 1,000,000 Earths and you would still be inside the solar system, drifting among the cold storage of comets that circle the sun in lazy centuries. Keep stacking. 1,000,000,000 Earths, then 10 billion. Somewhere around the 2 billion mark, you would finally cross the gap to Proxima Centauri. The tower would now be so tall that its base would have no memory of its summit. The lower planets would have cooled to frozen spheres long before the upper ones were added. Yet even this tower is only a local landmark. To reach the center of the galaxy by the same method, you would need to stack Earths until the tower stretched for 30 trillion diameters. The column would be so high that light itself, racing from bottom to top, would need a year to finish the journey. Somewhere along the way, the idea of stacking becomes absurd. The mind loses the thread. The image dissolves into pure number. Perhaps time is the more honest ruler. Let us slow the pace of light itself until it becomes visible. A photon, the smallest courier of light, crosses a football field in a heartbeat. If we could watch it, we would see a trembling speck of brightness taking one slow breath to travel from goalpost to goalpost. Yet that same photon, starting at one edge of our galaxy, would need 100,000 years to reach the other side. A single heartbeat becomes a cathedral of centuries. Civilizations rise, invent writing, forget the stars, and vanish while the same particle of light is still threading its way through spiral arms it will never comprehend. Our senses evolved to notice the leopard moving in tall grass, to judge the arc of a thrown stone, to sense the change of seasons, to love the warmth of a hand held in darkness. They did not evolve to register events that outlast glaciers. When we look up at night, the sky feels like a dome, a bowl inverted above us, and the moon seems closer than it truly is because our eyes read it as a thing about the size of a coin. The illusion is persuasive. It is also harmless until we try to step beyond the sky. Then the old intuitions fail, and we must choose between accepting a universe that dwarfs every human reference or retreating into the cozy fiction that the cosmos is smaller than it is. Yet there is no shame in this betrayal by the senses. Light years are not designed to be intuitive. They are simply the units that nature handed us. The gap between the Earth and the moon is already too large for instinct, but at least we can draw it on a page. The gap between stars is larger by a factor of 1,000,000, and the gap between galaxies larger again by a factor of 100,000. Each step up the ladder of scale requires a new surrender of familiarity, a new willingness to let numbers stand where feeling cannot follow. Still, something beautiful happens when we persist in the exercise. After a while, the absurdity itself becomes a kind of anchor. knowing that the car ride to Proxima Centauri would outlast every species that has ever lived on Earth, knowing that the stacked Earths would crumble under their own gravity long before they reached the galactic core, knowing that a photon needs 100 centuries to cross the starlit city we call home. Knowing these things does not alienate us from the cosmos. It binds us to it because the same laws that make distances unthinkable also make life possible. Gravity gathers atoms into stars, stars forge heavy elements, supernovae scatter those elements into space. Chemistry assembles them into beings who can look up and ask, how far away is that light? The question is small. The answer is larger than comprehension. Yet between the asking and the impossible reply lies a narrow bridge of wonder, sturdy enough to carry us from the warmth of a summer night to the edge of everything we can see. We may never walk a light year, but the light itself walks for us, carrying stories of places we will never touch. And so we let the photon be our pilgrim, the year be our yardstick, the heartbeat be our clock. We measure, we compare, we stack and we walk and we drive in imagination, knowing that the journey is not really about arrival. It is about keeping the questions alive, about refusing to let the vastness become a wall instead of a window. Out there beyond the last analogy, the light continues on its way, patient, silent, unhurried by calendars or hearts. Someday, perhaps, another mind will look back across the same gulf, trying its own desperate arithmetic of football fields and footsteps. If so, we are already in conversation, though the replies will be separated by epochs. The distance breaks our intuitions, but it cannot break the continuity of wondering. And that, in the end, may be the most human scale of all. The capacity to stand beneath uncountable stars and still feel the tug of a question that refuses to be measured by anything except the lifetime of a species willing to keep asking it. Imagine the sun as a single, steady lantern hung high above a midnight sea. Below it, the black water stretches farther than any eye has ever seen, and every spark of starlight we spy from Earth is another lantern, adrift on that same dark. Together, these lanterns form a loose, glowing wheel, a slow-spinning whirlpool of suns we call the Milaxy Way. To walk its length would take 100,000 years of light, yet even that number is only a label. Light does not hurry. It glides, it drifts. It carries pictures of the past. If we could ride beside a ray, we would feel nothing. No wind, no jolt, only the hush of centuries passing outside the window. So let us ride quietly and see the shape of our galactic home. Leave Earth behind, but keep it in mind. From here, the sun is a modest yellow lamp, one among billions. We rise above the plane of the galaxy, higher and higher, until the lamps gather into lanes, the lanes into arms, the arms into a pale disk. From this height, the Milky Way looks fragile, a child's toy flung across the dark. Yet its span is so wide that if every year were a footstep, you would stride for 100 millennia before crossing once. 100,000 light years edge to edge. Count them slowly, one per heartbeat, and your heart would beat for longer than human history has yet existed. Still, the galaxy spins, unhurried, one revolution every quarter-billion years. The sun, caught in that stately waltz, has circled the center some 20 times since the first sparks of life kindled on Earth. We are all riders on a slow carousel, clinging to a grain of rock, while the music of gravity keeps the horses in their paths. Draw a line from our lantern to the bright heart of the galaxy, and you trace a distance of 26,000 light years. That heart is a crowded place, stars pressed shoulder to shoulder, gas tormented by heat, and at the very core, a silence so deep it swallows light. We orbit that silence at 200 kilometers each second, yet we feel no breeze. The immensity cushions us. Between our sun and that center lie archipelagos of stars, scattered like towns along an ancient trade route. Some are nurseries where suns are born, others graveyards where suns have died. Messages older than the pyramids travel still in the form of starlight toward us from those distant burrows. When they arrive, the cities that sent them may have already crumbled into white dwarfs or ghostly nebulae. Distance is time. Time is memory. To map the galaxy is to read a diary written in fire. Now tilt the wheel. The Milky Way is thin on average, a mere 1,000 light-years thick, a ratio like that of a CD to its diameter. Stars wander a little above and below the midplane, like boats rocking on a calm lake. Our sun bobs through that lake, rising and falling every 60 million years or so, a lazy sine wave traced across eternity. When we rise, the density of nearby stars thins. When we sink, we return to a slightly busier street. None of this is felt on Earth. The planet's crust is too small, too local. Yet our motion is embedded in the greater tide, a tide measured not in minutes but in megayears. Picture the galaxy as a city seen from the air at night. The downtown core glares white with old, yellow suns. Spiral arms, avenues lined with younger, bluer lamps curl outward from the bustle. Along these avenues, gas clouds glow like neon signs, advertising the birth of new stars. We live in a quiet suburb halfway out on one of those avenues. From here, the downtown lights blend into a soft glow. We call it the Milky Way Band, a river of haze across our sky. On a dark night, away from terrestrial lamps, that haze resolves into a swarm of individual stars, each a distant window in the city's high-rises. Between the arms, lanes of darker blocks stand nearly empty, lots where streetlights have not yet been switched on. There, the night is deeper, the cold more intense. Travel those lanes and you might journey for hundreds of light years before meeting another star. Yet even emptiness is relative. Every cubic centimeter still holds a few atoms, the breath of ancient supernovae, the soot of expired suns. Consider the speed of thought. A neuron fires in a millisecond. In that instant, light races 300 kilometers, farther than London to Paris. Yet to cross the galaxy, even light must travel for 100 millennia. A single thought, repeated at each neuron, would echo through 100,000 years before reaching the opposite edge. The mind reels. Numbers become poetry, then become silence. We are left with metaphor, the only vessel large enough to hold such scale. Hold a coin at arm's length. The moon spans the width of your thumbnail. Shrink the galaxy similarly so that its 100,000 light-year disk fits inside a dinner plate. On that plate, the solar system is a mote of dust, smaller than a grain of cocoa, floating a fingernail's distance from the rim. And Earth, a bacterium on that mote. Yet upon that bacterium, minds look outward, tracing the spiral arms, naming constellations, writing equations, dreaming journeys. The dreaming is recent. A century ago, we still believed the galaxy was the universe entire. Now we speak of 2 trillion galaxies, each a distant echo of our own. But even alone, the Milky Way is roomy enough to break any sense of proportion. Pack every human who has ever lived shoulder to shoulder, and they would fill no more than a modest island. Pack every star in the galaxy at the same density, and you would need a continent of darkness between them. That darkness is not failure. It is the canvas on which stars are painted. Gravity stitches the emptiness with invisible thread, drawing gas into luminous clumps we name suns. Those suns burn quietly for millions, billions of years, then exhale metals back into the night: carbon, oxygen, silicon, the letters of future planets, future blood, future bone. We are the echo of that exhale. Every atom in your heart once trembled in the blast of a star that lived and died before Earth was born. Distance separated those atoms for eons, until gravity and chemistry gathered them here. Into you, into me, into eyes that can look back across the dark and wonder. Wonder does not need resolution. We map the galaxy inch by inch, photon by photon, yet the map remains unfinished. We still do not know the full shape of the outer arms. We still guess at the number of small stars too dim to see. We still feel the gravitational tug of something unseen dark matter, like an extra weight in the pocket of the city-bending street lamps we thought we understood. The questions keep the journey alive. Each measurement is a postcard mailed from the voyage. Wish you were here at 26,000 light-years from the center, bobbing gently above the mid-plane. We lick the stamp, press it to the envelope, and let light carry the message for us. Someday, perhaps, another mind on a distant planet circling a distant lamp will receive that postcard and read our greeting. By then, we may have changed beyond recognition. Our lanterns move to new positions in the wheel. Yet the address remains: third planet of a G-type star, spiral arm, western suburbs, Milky Way. So we return gently to the lantern we began with. The sun still burns, steady, patient. Its light takes 8 minutes to reach Earth, a distance we call 1 astronomical unit, a span so small that on the scale of the galaxy it does not even qualify as a hair's breadth. Yet from that modest lamp comes warmth, photosynthesis, poetry. Scale is not superiority. Small rooms can hold vast thoughts. 100,000 light-years of stars, gas, and darkness wheel above us every night, and we, the bacteria on the moat, give it a name, draw its arms on paper, plot our course across it as if plotting a crossing of the sea. The voyage is impossible for bodies, but not for light, not for thought. We have already sent ambassadors, radio whispers, golden records, robotic wanderers, creeping outward at the speed of a fast bullet, slower even than starlight. They will travel for tens of thousands of years before reaching the near suburbs of our galactic city. By then, the city will have rotated beneath them. Their destination will have drifted. They will still be ours, though no one who remembers them will remain. Distance dissolves memory, yet memory, encoded in metal and silence, may outlast the civilizations that forged it. Stand outside on the next clear night. Let your eyes adjust until the sky becomes a river of mute diamonds. Each photon that lands on your retina began its journey before you were born, some before humanity was born. The star that sent it may already be dead. Yet the message arrives, a final letter slipped under the door. Read it slowly. The letter says, "You are small, but you are not alone. You are fleeting, but you are part of a story larger than any lifetime." The galaxy turns like a great clock, and we are sparks caught in its gears, luminous for an instant, then gone. The clock does not mourn, it continues. New sparks ignite, old sparks fade. The arms sweep through the dark, carrying cities of stars we will never see. And somewhere, perhaps, another spark pauses, looks up, and wonders what lies beyond the glow. Imagine you could step outside the orbit of Pluto, far enough that the sun itself shrinks to a bright star among thousands. From that remove, the galaxy does not look like a swirl of equal suns. It looks frothy. Vast, interlacing bubbles of very nearly empty space, their walls glowing with the compressed gas and dust of 1,000 ancient supernovas. We, our Earth, our Sun, every photon we have ever measured, live inside one such bubble. A cavity 1,000 light-years across, its rim laced with the familiar jewels of the night sky: Sirius, Vega, Rigel, Arcturus. Astronomers call it the local bubble, and it is the room in which Earth has been listening to light since long before the continents had names. To grasp what this emptiness means, begin with something smaller. Hold your hand above a desk lamp. A few centimeters from the bulb, the air is warm. A few centimeters farther, it is cool. The lamp's heat reaches you, but the room itself changes how that warmth arrives. In the same way, the sparse vacuum of the local bubble changes every ray of starlight that reaches our telescopes. Light, remember, is patient. It may sail for 100 years, then spend a single week brushing against a wisp of hydrogen only a few atoms thick. That whispering contact nudges, colors, polarizes, and sometimes even diverts the ray. If we forget the bubble's gentle interference, our celestial tape measure slips by whole percentage points. Across light years, that is the difference between a neighbor and a stranger. The bubble was not always empty. 16 million years ago, give or take a cosmic heartbeat, a procession of massive stars near today's Scorpius Centaurus finished their brief, brilliant lives. One after another they burst, superheating their surroundings, driving expanding shells of gas that plowed into older, colder interstellar clouds. The bubbles merged, snowplowing matter into a dense, glittering rampart, while inside the merged shells, what remained was a rarefied calm. Only a tenth of the gas that fills the general galaxy. The Sun, drifting with its own entourage of planets, wandered into this excavated chamber a few million years later. We have been surfing its mild interior ever since, like a canoe gliding across the eye of a storm wider than a continent. Stand now at the center of this cavity, stand, that is, at the Sun, and look around. Every prominent star within 100 light-years is either a visitor like us or a native born of the denser folds on the cavity's rim. The Hyades cluster, a V-shaped knot of siblings only 150 light-years away, is the nearest detached piece of that rim. Their light, 625 years en route, passes through the bubble's thinned medium, arriving a little less reddened than it would if the full thickness of galactic dust still lay in the way. Farther out, the Pleiades sparkle inside a separate pocket of gas, their blue fires reflecting off local dust like frost on twilight grass. Between us and them, almost nothing. A vacuum more perfect than any laboratory on Earth, yet still carrying the faint metallic scent of ionized hydrogen. This emptiness is not sterile. It is merely quiet, and quiet changes everything. Interstellar medium is the universe's atmosphere. When it thins, starlight travels faster, straighter, less molested. When it thickens, light dawdles, dims, acquires a blush of dust-reddened color. Astronomers measure distance by comparing a star's true brightness with the brightness we receive. If they misjudge the intervening fog, they misjudge the star. Inside the bubble, the correction is small, but not zero. Neglect it, and our yardstick stretches like elastic. Correct for it, and suddenly nearby clusters tighten into crisp focus, their converging motions telling a story of past explosions and future orbits. The bubble, in other words, is not merely scenery. It is the lens through which we calibrate every farther mile of the cosmos. Yet even a lens has structure. Recent maps, stitched from ultraviolet starlight absorbed by the sparse gas, reveal tendrils and filaments threading the cavity, ghosts of older shells, corridors where the density rises, pockets where it falls almost to perfect vacuum. One of these corridors points toward the galactic plane, a tunnel perhaps 250 light-years long, offering an exit route for hot gas vented by past supernovas. Another, fainter, threads northward toward the constellation Taurus, a tunnel so tenuous that the universe itself seems to forget it exists. These veins matter. A star whose light arrives along a dense thread will appear farther than twin light that rode a sparser path. The universe, ever scrupulous, keeps its accounts, but we must learn to read the ledger. So we send new scouts. The European Space Agency's Gaia satellite, now in its second decade, is measuring 1 billion stellar positions to the width of a human hair seen from the moon. Its catalog folds in the bubble's subtle refractions, trimming uncertainty to the width of a few solar systems. Future missions, already sketched on quiet whiteboards, propose to go further. A constellation of small satellites, flying in precise formation, could watch how starlight scintillates, twinkles, when denser clots of gas drift across the line of sight. From that tremble, we will infer the clump's shape, mass, and motion, filling in the last blank pixels of our local map. Others dream of launching a simple spectrograph on a solar sail craft that would drift outward, spiraling through the bubble's walls, tasting the gas directly, returning spectra no telescope on Earth can record. We would learn, grain by grain, how much of the bubble's substance is pristine hydrogen and helium, how much is the recycled ash of exploded stars, how much is the carbon and oxygen that one day will become planets, oceans, living breath. While we wait for those wanderers, we listen with ears of light already en route. Some of the bubble's gas is ionized, stripped of electrons that wander free, jostling passing starlight. The jostling polarizes the light, aligning its waves like schools of fish turning in unison. Measure the polarization, and you measure the invisible magnetism threading the void. Those fields in turn tell us how cosmic rays, atomic nuclei moving near light speed, spiral through the neighborhood. When a cosmic ray rides a magnetic curve and slams our atmosphere, it releases a shower of secondary particles, a gentle rain that has been falling on Earth since life began. The bubble's magnetic arches steer that rain, turning what looks like empty space into a slow, invisible weather system whose whims may influence cloud cover, mutation rates, the very tempo of evolution. We live inside a room whose walls we cannot see, but whose ventilation shapes the tide of days. Consider the Hyades again. Their collective light travels across the bubble, arriving a little bluer, a little sharper than it would if the space were thick. Astronomers compare that light with the light of stars embedded in the bubble's wall. The comparison reveals distance by parallax, but also by color shift, a second opinion that tightens certainty. When the two methods agree, we know the bubble's transparency within 1%. When they differ, we discover a hidden clot of dust, a pocket we had overlooked. Thus the bubble is not merely a void. It is a laboratory, and every star is a probe. Every photon is a data point, every spectrum a sentence in a story older than the hills. And the story is still unfolding. The sun drifts onward, carrying us toward the constellation Hercules at 20 kilometers each second. In 30,000 years, we will exit through the bubble's fluted wall, emerging into the colder, thicker medium beyond. The stars ahead will dim and redden, their light obliged to push through fresh corridors of dust. Behind us, the bubble will recede, a memory of spacious rooms. Our descendants, if they still watch the sky, may find their calibrations shifting, their cosmic yardsticks elongating. They may speak of a time when the stars stood clearer, nearer, a forgotten age of open skies. Until then, we are privileged tenants of an airy suite carved by ancient suns. Tonight, step outside and locate the Pleiades, that little knot of silver above the horizon. Their light left those fires 4 centuries before your gaze. Between there and here, it crossed the bubble's gentle vacuum, a thread stretched across emptiness finer than any spider's silk. Yet that thread is long enough to contain every human heartbeat that has ever beaten. Hold the thought. Feel how distance is not merely emptiness. It is structure, memory, the invisible architecture that lets light arrive at all. We live inside a fragile chamber, and every measurement we make is also a love letter to its walls. So far, we have watched starlight that was born when Shakespeare still dipped his quill, and we have felt the hush of photons that set out before our continents took their present shape. Yet even these leaps across centuries feel modest when we step back one more pace and let the stars themselves gather into swarms. Suddenly, the mileposts are no longer single suns, but congregations of hundreds, of thousands, of millions. And the word distance stretches like morning fog until the mind loses sight of its edges. Begin with something you can still see without leaving your own sky. On a winter night, if you follow Orion's belt upward, you will meet a faint clutch of blue-white gems known since Babylonian scribes first pressed cuneiform into clay. To the eye, they are a tiny question mark. To the Galilean spyglass, they resolve into dozens, then into hundreds, each star so young that its hydrogen burns with the impatience of adolescence. This is the Pleiades. 440 light-years is all that separates us from those newborn suns. A lighthouse beam could cross that gulf in 4 centuries. A fast human craft would need millions of years. Still, in the ledger of the galaxy, the Pleiades are practically next door. They are an open cluster, a family that has not yet left home. Gravity still hugs the siblings together the way a quiet courtyard still holds the laughter of children long after sunset. Travel farther and the family portrait changes. Beyond the thin veil of nearby open clusters lies a second population, spherical, ancient, and immense. They are called globular clusters, though the name hardly prepares you for what they are. Imagine taking a scoop of 250,000 stars, each one older than Earth's mountains, and compressing them into a ball only a few hundred light-years across. Their orbits do not politely circle the galactic plane like ours. They dive through the Milky Way's outer halo on elongated trajectories, apogees so distant that the Milky Way's spiral arms shrink to a faint glow in their rear-view mirror. When we intercept their light, we are eavesdropping on messages dispatched in an era when Earth's crust was still too soft to preserve a fossil. How do we know how far away such things are? Hold a match at arm's length and its brightness is a clue to its distance, but only if every match were identical. Stars are not identical, yet they do carry a standard candle in their cores. Hydrogen fuses at a predictable rate, and the pressure of that furnace dictates how bright a star of a given temperature will be. Plot enough ordinary stars, and you find a narrow, slanted line called the main sequence. Slide the line up or down until it overlays the stars you see in a distant cluster, and the amount of sliding required tells you, without ruler or radar, how far the cluster must be. The trick is older than the word computer, yet it still anchors our cosmic surveyor's kit. Astronomers call it main sequence fitting, a calm phrase for an act that quietly rewrites geography on the scale of galaxies. With distance comes age. Open clusters like the Pleiades are delicate. After a few 100 million years, the gravitational tides of the galaxy tug their members apart like dancers scattered by a sudden storm. The survivors drift away as solitary field stars, carrying within them the heavy elements forged in the brief lives of their brightest siblings. Globular clusters, by contrast, are ancient cathedrals. Their stars formed when the universe itself was young and metal-poor, so their interiors preserve the chemistry of the early cosmos. The older the cluster, the more its brightest stars have already burned out, leaving only cooler, dimmer suns. Measure the temperature at which the main sequence bends upward toward the red, and you read off the hourglass sand that has already fallen. Thus distance and age are entwined like melody and lyric in the same song. Stand inside one of these clusters, if your imagination will grant you immunity to radiation, and the night would be beyond anything earthly. In the core of a globular, the average gap between stars is a few light-weeks, not light-years. Sirius would hover where Neptune now orbits, dazzling the retina with the white of Arc-Welders sparks. Yet for all their crowding, these clusters remain stable over eons, a testament to the delicate balance between kinetic energy and gravitational embrace. They are laboratories where gravity performs experiments too slow for any human laboratory to witness. They are also archives. Every star retains the pristine gases it acquired at birth, except for the thin skin altered by its own fusion. By reading the absorption lines in their spectra, we recover the composition of the infant universe, long before Earth had even a hypothetical existence. There are mysteries here we have not yet cracked. Some globular clusters contain stars that appear younger than the universe itself, yet older than their neighbors. Did they form in a second burst? Did they strip material from passing companions? We do not know. Other clusters show signs of multiple generations, contradicting the old belief that all their stars hatched at once. The mathematics of self-gravity says they should have collapsed into massive black holes, yet many still parade their stars proudly. Something, perhaps magnetic fields, perhaps unseen dark matter, holds them up. We catalog the questions and keep observing, because every answer redraws the map of what is possible. Step back once more and clusters themselves become specks. The Milky Way hosts a few hundred globulars, a few thousand opens. Beyond our spiral, the Andromeda Galaxy holds its own retinue. Telescopic eyes look out into the Virgo supercluster and find that every galaxy of sufficient mass keeps a similar court, as if the universe itself insists on this particular form of ornamentation. The distances between neighbor galaxies are measured in millions of light years, but the distances between their attendant clusters are still measured in mere hundreds of thousands. Thus clusters form a kind of scaffolding, a lattice whose spacing tells us how dark matter once pooled in the early universe, where gravity had slightly more grip than elsewhere. They are fossils not just of chemical history but of cosmic architecture. And so, in the quiet of an observatory night, while motors hum and shutters blink, a researcher compares two photographs taken decades apart. The stars of a globular cluster have moved, barely. A pixel's drift across the detector translates to a velocity slower than a garden snail on Earth. Yet that snail's pace, multiplied by the depth of time, reveals the cluster's true orbit around a galaxy we may never reach. From such minute shifts, we infer the mass of the invisible halo, the distribution of dark matter, the future collision course of entire galactic cities. All from a motion so small that a snowflake settling on the telescope dome would have spoiled the measurement. What does this do to the heart? We began with the Pleiades, a stone's throw in galactic terms, and we have followed the ladder of clusters until a million light years felt like a unit on a ruler. At every rung the past grows heavier, the future more diffident. Yet the same laws that govern a dropped apple govern the slow waltz of these starry swarms. Somewhere between the backyard and the void, the mind slips into a peculiar calm. The universe is vast, but it is not random. Patterns repeat. Gravity writes the same poem at every scale, only the paper changes. If you find yourself beneath a dark sky after hearing this, look again at that little knot of blue. The photons striking your retina left the Pleiades around the time Galileo first turned his tube toward Jupiter. They have been racing across the vacuum for 4 centuries, past dust and planet, moon and satellite, to end their journey on the back wall of your eye. Consider that the next time you exhale, your breath will mingle with air that was once inside a dinosaur. And the iron in your blood was forged in a star that did not even belong to our solar system. Clusters are the postmen of such iron, dispersing it when their massive stars detonate, seeding the galaxy with the only ingredients that could ever make blood or bone or thought. We have not yet spoken of the great walls of galaxies, the voids where nothing seems to live, the filaments that stretch across billions of light years. To reach them, we must leave the comfortable porch of clusters and step into the true wilderness. But our feet are now accustomed to the dark, and our eyes have learned to read starlight as if it were a diary. Close them for a moment and feel the hush. Somewhere a globular cluster is plunging through the halo of our galaxy, carrying its cargo of ancient suns. Somewhere an open cluster is breaking apart, releasing its stars like dandelion seeds into the galactic wind. And somewhere, perhaps, a planet orbiting one of those wandering suns has just tilted its poles toward its star, beginning a spring that no human will ever witness. Let that thought settle. We will need its weight, for the next step takes us beyond even the clusters, beyond the halo, beyond the local group, into the intergalactic dark where distance itself begins to lose its everyday meaning. Out beyond the final wisps of the Milky Way's glowing halo, the darkness is not empty. It only looks vacant because the lanterns of entire galaxies hang so far apart that their combined glow is reduced to a frost of pale smudges in our night sky. To see them properly, we must loosen our grip on the scale that already strains the mind. Kilometers, planetary orbits, even the span between stars. Now we step outward again, from star hops of a few light years to voyages measured in millions. On this scale, even light, fast enough to circle Earth 7 times in a heartbeat, must travel for epochs that dwarf the whole human story. Yet travel it does, carrying across the void the evidence that we belong to something larger than a star city. We belong to a neighborhood of galaxies, drifting islands of suns whose mutual gravity writes slow, majestic choreography across the cosmic ocean. Begin with the nearest, Andromeda. In a dark countryside, the unaided eye sees her as a faint, elongated star. She looks quiet, almost delicate. In truth, she is a colossal spiral containing 1 trillion suns, twice the stellar population of our own Milky Way, packed so tightly at her core that stars sit only light towers apart. She is approaching, not quickly by earthly reckoning, about 100 kilometers every second, but steadily, inevitably. In 4 billion years, her tide will stretch and fold our spiral arms until both galaxies swirl into a single, bloated ellipse astronomers already call Milkomeda. On that future night, a descendant sky will blaze with unfamiliar constellations, and the Milky Way's broad river will be replaced by a warm, pearly dome. Yet even this collision will be gentle in the way that clouds merge. Stars are so small compared with the emptiness between them that few, if any, will actually touch. The architecture of the heavens will be rewritten, but the atoms of planets and people will remain untouched. Between us and Andromeda lies a scattering of lesser companions. The Triangulum galaxy glimmers at just under 3 million light years, a slightly smaller spiral whose arms are more open, more lace-like. She, too, moves under gravity's long reach, though whether she is merely passing or bound in a dance with both us and Andromeda is still uncertain. Observations hint that Triangulum may already have brushed Andromeda once, a near miss that stripped gas into looping streams of hydrogen now colder than the surface of Pluto. Such encounters remind us that galaxies are not solid objects but gravitationally laced clouds, their shapes as malleable as smoke when tugged across eons. Closer still, the Milky Way is attended by a court of dwarf galaxies, cosmic fireflies orbiting in extended, lazy paths. The large and small Magellanic Clouds, visible as soft glowing patches from Earth's southern hemisphere, are the brightest of these. Each is modest by galactic standards. The large cloud holds only 10 billion stars, the small about 3. Yet their passage through the Milky Way's outer halo ignites bursts of star birth, nebulae glowing like pink coral in a midnight sea. Tidal friction has already torn one long ribbon of gas from them, the Magellanic Stream, stretching across a quarter of the night sky, though it remains invisible to human eyes. These dwarfs are destined eventually to merge with us, a slow accretion that will widen our spiral and seed fresh suns in the outer disk. Dozens more dwarfs circle us in dark-skied anonymity. Names such as Draco, Sculptor, Fornax, and Carina belong to collections of stars no larger than a globular cluster. Yet each is a galaxy in its own right, wrapped in its own shroud of dark matter. They drift through the outer halo like autumn leaves on a pond, their motions recording the gravitational fingerprints of events long past, ancient mergers, close passages, the slow gathering of the great spiral we now inhabit. Most are so diffuse that a spaceship flying through them might cruise for centuries between stars, surrounded only by the faint glow of distant campfires no brighter than Jupiter in Earth's sky. To grasp these distances, fold time into space. A child who turned on a flashlight the moment the first apes walked upright would now see that beam reach the large Magellanic Cloud. Barely. The light we intercept today from Andromeda left when Australopithecus gazed across an African savanna, unaware of any cosmos beyond the next watering hole. Triangulum's photons began their journey when stone tools were humanity's freshest invention. Every photograph of these galaxies is therefore an ancestral letter, delivered after a courier crossed a chasm of dark and silence longer than any mountain range on Earth. Gravity, though, ignores the delay. It acts instantly across the light years, binding galaxies into a sprawling family we call the local group, all its members whirling within a radius of roughly 10 million light years. Beyond this clan, the universe arranges itself into looser federations. The Sculptor group, the M81 group, the sprawling Virgo supercluster whose core lies 60 million light-years away. Step farther, and even superclusters dissolve into the froth of the cosmic web. Walls and filaments of galaxies surrounding voids so wide that their interiors could swallow 1,000 Milky Ways side by side. Imagine, then, the task of crossing even the smallest of these gulfs. A craft traveling at the speed of our fastest planetary probes would need 20,000 years to reach the nearest star. Multiply that by 500,000 to arrive at Andromeda. The numbers outrun language. They leave only metaphors of breath against a hurricane. Yet light itself makes the journey in a twinkling, and in doing so teaches humility. The universe is not unreachably large because it is hostile, but because our lives are calibrated to the rhythms of continents and seasons, not to the patient pulse of galaxies. Still, the mind wonders. Could a future species, perhaps no longer biological, ride the gravitational currents between galaxies the way Polynesian navigators once rode ocean currents between islands? Dark matter's invisible topography would be their reef, the occasional rogue star or gas cloud their resting place. Energy might be sipped from the hawking glow of small black holes, or harvested from the faint cosmic microwave background that still bathes all space. Such voyages would unfold over billions of years, but time itself is negotiable to entities who measure existence in geological patience. They would arrive changed, unrecognizable to their ancestors, bearing memories encoded in stable islands of dark matter or in the quantum spins of interstellar ice. For now, we remain earthbound, tracing orbits on the parchment of a single spiral arm. Yet every clear night invites us to look up and acknowledge the neighbors. They hover like lanterns seen across a darkened lake, reminding us that emptiness is only distance, not absence. Their gravity has already brushed our lives, tugging the sun ever so slightly, writing faint ripples in the cold dust that will one day become new worlds. We are participants in a slow waltz whose music is played by the mass of 1 trillion suns, a melody that will continue long after the last human name has been forgotten. Out there, the light years accumulate like unread pages in an immense book. Each photon that lands on a telescope mirror is a syllable from a sentence begun before our planet had trees. To measure these distances is to calibrate our place in a story still being written in a language older than any rock on Earth. And somewhere in the hush between heartbeats, we may sense the turning of those enormous chapters, the quiet invitation to read on, to follow the words across the void, beyond the next margin of night. A single beam of starlight can feel almost intimate when it lands on your eye, as though the universe is leaning in to whisper a secret. Yet that whisper began its journey before your hometown existed, before the sun had even coaxed Earth into a cradle of oceans. The photon that brushed your retina left its source when our world was still forging its first rocks, and it spent the intervening eons racing through an ever-widening gulf of emptiness. That widening is not a minor detail. It is the very architecture of cosmic distance, the reason a light year is more than a tidy measurement. It is a living record of expansion. Imagine, for a moment, standing on a calm lake at night holding a paper lantern. When you set it adrift, The lantern drifts a few boat lengths, carried by slow currents. But suppose the water itself swells while the lantern floats. Waves spread, the shoreline recedes, and when you finally measure the distance traveled, you find it far exceeds what the lantern could have managed on still water. Starlight swims through space in much the same way. Between departure and arrival, the cosmic lake has swollen, stretching the very fabric on which the light rides. We call the stretching redshift. The ancient waves are tugged so thin they arrive at our telescopes longer, cooler, redder than when they set out. The degree of reddening is a gentle but precise indicator of how long the journey took, how much the universe has aged, and how far the lantern has drifted. Edwin Hubble first noticed this reddening, not with lanterns but with galaxies, whole continents of stars sailing away from us in every direction. The farther they appeared, the faster they receded, a simple proportion as reliable as a heartbeat. That proportionality, Hubble's law, is the quiet pulse of the cosmos. Recessional speed does not arise from galaxies striding through space. Rather, space itself is multiplying between them, an endless creation of new room. Picture two buttons sewn to opposite ends of an elastic ribbon. Pull the ribbon and the buttons move apart without crawling a millimeter across the fabric. The ribbon grows, carrying the buttons with it. Likewise, every point in the universe sees itself as the center of the expansion, not because of vanity, but because every patch of space is knitting more space around itself. The numbers quickly outrun everyday intuition. A galaxy whose starlight began toward us when the universe was a tenth its present age now glows in our sky, reddened so severely that its ultraviolet features have been pried all the way into the infrared. The photons themselves have not changed. They are identical to the instant they leapt from a young, blue sun. What changed is the ground beneath them, a cosmic treadmill that lengthened their stride. Our instruments read that stretch and translated it into a distance, perhaps 7 billion light-years, perhaps 10. Yet those numbers are not tape measure lengths, they are look-back times, records of how long the journey took. The galaxy may now lie 30 billion light-years away, carried deeper into the dark by continued expansion. Light years, therefore, serve two masters. They tell us how stale the news is, and they hint at how wide the stage has become since the news was fresh. Cosmologists draw a careful distinction. Look-back time is the stopwatch reading, how long the light has been traveling. Proper distance is the separation between 2 points measured at a single instant, a cosmic snapshot. Both are valid, but only the latter describes the true span of the present-day universe. Calculating that span requires us to fold together the expansion history, the changing pace of growth, the push and pull of matter, radiation, and the enigmatic influence we call dark energy. The sum total of those calculations yields a bewildering result. The observable universe is roughly 92 billion light-years across, even though the universe itself is only 13.8 billion years old. The universe is older than it is wide, because width is measured in the stretched fabric of today, while age is measured on the watch that rode with the light. At the limit of observation lies the particle horizon, the most distant shell from which any signal, even in principle, could have reached us since the Big Bang. Beyond that shell, the expansion carries regions away faster than their light can close the gap. The horizon sits about 46 billion light-years away in every direction, a sphere of causality, and everything within it composes the known. Yet the known is not all that exists. It is merely the patch swept clean by our particular past light cone. Other observers elsewhere in the cosmos possess their own spheres, overlapping or disjoint, forever beyond our reach. Infinity may teem with such bubbles, each a private atlas of the sky. Contemplating these horizons stirs a peculiar vertigo. The farther we peer, the closer we approach the furnace of the Big Bang, until at last we sight a wall of glowing fog. The cosmic microwave background, the oldest light. It broke free when the universe cooled enough for atoms to form, releasing a snap of radiation that still washes over every cubic centimeter of space. That wall appears at a look-back time of 13.8 billion years, yet it is not a wall in the usual sense. It is the edge of time, a horizon of visibility, not of substance. Beyond it, earlier light could not travel freely. The cosmos was opaque, a roiling plasma. Thus, even our most perfect telescopes cannot penetrate to still earlier epochs using light. We must rely on subtler messengers, neutrinos, gravitational waves, the faint fossil scars imprinted on spacetime itself. Pause to notice how expansion skews every cosmic clock. The light year is not a fixed rod, it is a pliable thread. When the universe was half its present age, a light year occupied less space, so events unfolded in a smaller arena. A star that lived and died 10 billion years ago performed its whole drama in a cosmos compressed, its future light years still embryonic. We see the finale as a pale, redshifted glimmer, but the star itself never knew the vast distances its photons would one day traverse. Distance, then, is retrospective, stitched together in our present by patient light and patient mathematics. There are quiet implications for destiny. If expansion continues to accelerate, distant galaxies will eventually redshift beyond detectability. Their light will still journey toward us, but space will stretch so fast that the waves cannot complete the crossing. One by one, the islands of light will wink beneath the horizon, until only the nearby, gravitationally bound precincts remain visible. A future astronomer born in 1 trillion years might scan an empty sky, unaware that galaxies once blazed in every direction. All evidence of cosmic history will have slipped beyond the cliff of redshift, leaving only a void of fading embers. The universe will seem smaller, lonelier, though in truth it will be larger than ever. For now, we inhabit a privileged moment. Enough expansion has occurred to sketch the grand structure, yet not so much that the ink has faded. We can still measure the redness of distant starlight, still trace the choreography of galaxies, still feel the echo of primordial fire. Each measurement is a small act of preservation, a promise that what we learn today will outlast the stars that supplied it. Knowledge, unlike matter, is not diluted by expansion. It rides a different current, passed from observer to observer, refined, questioned, cherished. And so a light year becomes more than a unit. It is a thread that stitches human curiosity to the edge of time. A reminder that the same law of swelling space which stretches starlight also stretches possibility. Every photon that lands on a telescope mirror carries a tale of distance rewritten by cosmic growth, a tale that invites us to imagine what lies beyond the horizon of visibility, beyond the reach of any future signal. We may never touch those realms, yet thinking about them enlarges the interior map of the mind, a map measured not in kilometers but in wonder. Somewhere, further upstream of time, another civilization may be gathering its own data, puzzling over the same reddened glows, drawing its own sphere of sky. Their physics will echo ours because expansion is impartial. It stretches all light, all space, all dreams. If their instruments are acute enough, they too will discover that the universe is older than its radius, that distance is a story still being written. And in that shared recognition, separated by billions of parsecs and untold cultural paths, lies a quiet kinship, two brief sparks, each trying to read the same vast script. The night deepens. The last measurement is logged, the shutter closes, and the telescope exhales into darkness. Somewhere in the data, a number records the redshift of a galaxy whose name no tongue will ever speak. That number is a footprint on a beach that grows wider with every tide. Tomorrow the tide will return and the print will seem fainter, but the shape of what we learned will remain, folded into the expanding lattice of human understanding. We close the file, step outside, and look up. The sky is calm, the stars are steady, and the space between them is silently blooming, carrying their ancient light across the widening dark, toward whatever minds are ready to receive it. Imagine a single photon. It has no rest mass, no color, no weight you can feel in your palm, yet it has been racing across the cosmos since before any star was born. For 13.8 billion years it has flown, unhindered through expanding space, slipping between emerging galaxies, brushing past dark clouds of hydrogen, climbing the growing walls of void. Tonight it finally ends its journey when it lands, gently, almost shyly, on a detector aboard a small spacecraft orbiting the third planet of an ordinary yellow star. We call that photon a piece of the cosmic microwave background, and its arrival is the closest thing we have to touching the Big Bang itself. To speak of light years is usually to speak of distance, but with these ancient photons, it is more honest to speak of endurance. They have not simply crossed trillions upon trillions of kilometers. They have outlasted every mountain that ever stood on Earth, every ocean that ever lapped against young continents, every breath that ever stirred a living lung. When the temperature of the universe dropped 3,000 degrees Kelvin, these photons broke free from the searing fog of hydrogen and helium, stepping into the open like children released from school. Space kept stretching, cooling, darkening, and the photons stretched with it, their wavelengths growing from fierce white to dull red to invisible microwave hush. They have been cooling ever since, and we now receive them at a temperature only a few degrees above absolute zero, barely warmer than the void itself. Think of that moment of release. It happened everywhere at once, yet from our vantage it appears as a distant surface, a sphere of last glow we name the surface of last scattering. If you could stand outside the universe and watch, you would see that surface retreating in every direction at the speed of light, a ghostly balloon whose skin is the oldest photograph ever taken. We live inside that photograph. Every room you have ever sat in, every night sky you have stared up at, is permeated by this fading flash. It washes over you while you sleep, slides across your skin on a summer afternoon, drifts through the glass of your window as you sip tea. You are bathed in the cooling embers of creation, and you never notice. How do we measure something so tenuous? We build instruments that know how to shiver. Bolometers, radiometers, horns of metal tuned to a whisper 6 octaves below the lowest note your ear can hear. We lift them above the dampening air, on balloons above Antarctica, on satellites beyond the moon, on a telescope parked at Earth's second Lagrange point where sunlight is muted and the sky is always midnight. We map the temperature of the glow, not once but millions of times, until we can see differences of a few millionths of a degree. Those minute bright spots are the seeds of everything that will ever become. Galaxies, clusters, great walls of galaxies, the filaments and voids that give the universe its texture. The cold spots are the ancient valleys where matter would later drain and collapse. We read the sky the way a forensic scientist reads blood spatter, tracing the story backwards to the instant of violence. And what distances are written there? When the light began, the entire observable universe was smaller than the orbit of Mercury, crammed to densities that make leads seem like smoke. Today the same region spans 90 billion light-years across, swollen by the quiet, inexorable breathing of space itself. Between then and now, the cosmos doubled its size again and again, each expansion stretching the photon's waves, turning gamma glare into microwave lullaby. If you could fold that history onto a single Earth day, the photons broke free at 11 picoseconds past midnight. The first stars would not spark until well after noon. Dinosaurs appear at 11:59 and 45 seconds. Your life lasts less than the final heartbeat of the final second. Yet the photon endures, a courier from the true morning of time. We once believed the universe might be infinite and eternal. The existence of this dim glow proves otherwise. There was a beginning, a moment when space itself was packed so tight that light could not travel without being scattered like sunlight in fog. Then came the moment, 380,000 years after the beginning, when fog lifted and light could run forever. We are the descendants of that moment, built from the atoms that condensed later, lit by stars that formed from the slight excesses of temperature we now measure in the sky. Every carbon atom in your hand, every oxygen atom in your next breath, was once a perturbation in that primordial sea, a ripple 1 part in 100,000 brighter or cooler than its neighbor. We are calibrations of the cosmic glow, brief assemblies that learned how to look back and read their own birth certificate. Still, mysteries remain. The glow is too smooth on the largest scales, as if distant regions on opposite sides of the sky had conspired to match temperatures to better than 1 part in 10,000. Something stretched them apart before the fog lifted, a brief, violent expansion we call inflation, faster than light, faster than thought. We see its fingerprints, but we do not know the hand that pressed them. Dark matter, dark energy, the exact shape of space, all are encoded in the subtle swirl of polarization that threads the glow like silk. We have maps, but we do not yet have the legend that deciphers every line. So we keep listening. Night after night, detectors colder than the photons themselves stare into the dark, integrating silence, waiting for the next ancient messenger. Each photon is a postcard addressed to no one in particular, written in a language of temperature and angle. Together they tell us that distance is not merely the space between things. It is the time required for light to be molded by expansion, stretched like taffy, shaped by gravity, handed down across epochs. A light year is not just 9 trillion kilometers. It is the distance that memory can travel without being lost to the growth of space itself. When you next step outside, look up at the patch of sky above your roof. From that tiny window, thousands of these photons are arriving every second. They have outlived every civilization, every species, every mountain range that ever rose and crumbled. They carry no banner, no anthem, no creed. They are simply the cooling breath of the beginning, and they fall on you without judgment. Let them land. Feel the hush they lay across your thoughts. In that quiet, consider how far they have come, how long they have traveled, how completely they have outpaced every attempt at permanence. Then gently let the moment go. There are older distances still to measure and deeper silences still to hear. Imagine a lighthouse whose beam can be seen from the far side of the planet. Now imagine that the lighthouse is smaller than a single grain of sand, yet its flash outshines every city on Earth combined. Such a thing should not exist, yet the sky is full of them. We call them quasars, short for quasi-stellar radio sources, a name that once fooled us into thinking they were lonely stars. They are not stars. They are the ferocious hearts of infant galaxies, the most distant lighthouses in the cosmos, and they break our habit of measuring distance by the gentle rules we learned at home. Begin with something familiar. A candle across a darkened room appears dimmer the farther you step away. Measure how faint it looks and you can guess the span between you and the flame. Astronomers call this the standard candle trick, and it has served us for a century. But a quasar is no candle. It is a bonfire fed by a black hole as massive as 1 billion suns, devouring so much gas that the friction glows brighter than the entire galaxy that hosts it. Brighter, in fact, than every star in our home supercluster put together. Because their glare is so extreme, we can see them staggering distances away, farther than any other single object. Yet that same brilliance makes them unreliable rulers. A quasar can dim itself by turning its voracious mouth away from us, or it can blaze suddenly if a new star cluster drops into the trough. The light varies not by the calm pulse of a stellar heart, but by the violent mood swings of an accretion disk swirling at half the speed of light. So the simple inverse square law we trusted on Earth dissolves into uncertainty. We are left holding a tape measure whose markings keep slipping. How, then, do we tether these beacons to a distance? We listen to the voice of the universe itself. As the quasar's light crawls across the expanding fabric of space, every inch of that fabric stretches, pulling the waves longer and redder. The farther the journey, the more the light reddens. We read the shift like a barcode printed on ancient photons. Redshift 7 means the waves have doubled in length once for each billion years of travel, until they arrive at Earth stretched by a factor of 8. That corresponds to more than 13 billion light-years, a number so large it feels weightless. But think of it this way. The flash we catch tonight set out when the universe was a toddler, less than 800 million years old. Every atom that would ever become your breakfast cereal, your pet, the ground beneath your shoes, was still folded inside a cosmos less than a tenth its present size. The quasar's glow has been racing through stretching space ever since, a courier bearing headlines from the morning of time. To anchor that redshift in something we can weigh and count, astronomers hunt for narrow dark lines etched into the quasar spectrum. These are the fingerprints of cold gas lying between us and the beacon. Hydrogen, the primordial element, absorbs its own favorite color, leaving a tiny gap. In a nearby star, the gap appears in ultraviolet. In the quasar spectrum, it has been nudged all the way down to the infrared. Measure the nudge and you have measured the expansion that carried the light across the gulf. Each absorption line is like a postmark smeared by cosmic expansion. And because the smear is cumulative, the most distant lines arrive looking almost unrecognizable. Yet they still whisper the same story. Space has grown, and the quasar is older than any geography we can visit. Inside those early galaxies, black holes grew with shocking speed. A hole weighing 1 billion suns should take forever to assemble, yet we find them already in place when the universe was barely 5% of its current age. How did they gorge so quickly? We still carry no consensus answer. Perhaps the first stars collapsed into seeds that were already obese. Perhaps gas flows converged in torrents, feeding a black hole the way snow rolling downhill becomes an avalanche. Whatever the mechanism, the presence of such massive engines so early tells us that the quiet picture of gradual cosmic growth we once sketched is too gentle. The infant universe was a place of violent miracles. And here the idea of a light year itself begins to quiver. A light year is the distance light can trek in one Earth year, but the runway beneath those photons is stretching even as they run. When we say a quasar lies 13 billion light years away, we do not mean it took 13 billion years to reach us. It took less, because the space it crossed was smaller at the beginning of the journey and grew larger only after the light had already traveled partway. The quasar's present distance, if we could halt the expansion and lay down a cosmic tape measure, is more like 29 billion light years. So which number do we choose? The answer depends on whether you are asking how long the light traveled, how far the light traveled, or where the quasar would be found today. Our familiar mile marker dissolves into 3 separate answers, each correct in its own coordinate system. A quasar forces us to admit that distance itself is a question of perspective in an expanding cosmos. Stand beneath a moonless sky far from city glare, and you will see the faint band of the Milky Way. If you could peel your eyes to infrared sight, that band would explode into a sea of other smears, each the blended glow of countless suns. Among them, a handful of tiny crimson specks would betray the quasars, rosier than anything nearby. They look serene, but each is a maelstrom. A black hole spins, dragging space itself like thick syrup caught on a spoon. Magnetic fields braid, snap, and fling jets outward at nearly light speed, boring tunnels through the galaxy's gas. When the jet points toward us, we see a searchlight. When it swivels away, the quasar dims and we may mistake distance for disposition. Variability on the timescale of months, weeks, even days tells us the emitting region is no larger than our solar system. To outshine a trillion suns from such cramped quarters is to push the laws of physics to their luminous limit. If you scooped a cup of that accretion disk, its glow would vaporize mountains. Yet the cup itself would weigh no more than morning mist, so diffuse is the superheated gas. Extreme conditions make a mockery of everyday intuition. Because quasars are visible so far away, they double as backlights for whatever lies between. Clouds of neutral hydrogen, thin smears of metals forged in the first stars, even the invisible filaments of dark matter leave shadows in the beam. By stacking thousands of quasar spectra, astronomers map the cosmic web, the ghostly scaffolding on which galaxies later clustered. In this way, a beacon from the edge of time becomes a flashlight for surveying the darkened rooms of the universe. Each spectrum is a chapter of a story written in fire and absence, and we read them line by line, piecing together a census of stuff we can neither see nor touch directly. Still, mysteries accumulate faster than answers. Why did quasars flourish so exuberantly when the universe was young, then fade to relative quiet by middle age? Is their apparent absence in the modern cosmos a sign that most black holes have already eaten the gas within their reach, or merely that they dine more discreetly? We find far fewer quasars nearby than far away, implying that the early universe was a more flammable place, rich in raw fuel. Yet we do not fully understand how that fuel reached the centers of galaxies so quickly, nor why the feast ended. Perhaps supernova winds and relativistic jets blew the larder doors shut, or perhaps the cosmos simply diluted its pantry as expansion scattered the gas. Whatever the cause, the quasar era now lies more than 10 billion years behind us, a brief but spectacular adolescence in the lifetime of space. As you listen, notice the hush between thoughts. That hush is itself a traveler, a wave of quiet that has crossed the same expanding gulf as the quasar's light. Sound does not carry through space, yet the metaphor holds. Every pause in our understanding is a silence that has journeyed toward us across dark and growing seas. We stand at the shoreline, cupping an ear to waves that arrived only this instant, though they stirred when the earth itself was still forming. Each discovery lengthens the beach, each new question deepens the water. The quasars remind us that every measurement is also a memory, and every memory is already ancient by the time it touches the mind. So the next time you look up and feel the sky to be a fixed dome, remember the quasars. They are not decorations pinned there for our comfort. They are urgent telegrams, pressed into envelopes of light and sent racing across an expanding canvas. They arrive bearing witness to a time when the universe was raw, when black holes grew like weeds, when the first galaxies were forging their identity in fire. They stretch our definitions of distance until those definitions fray, forcing us to trade simple miles for expanding spacetime, for look-back time, for moving coordinates. In doing so, they nudge us toward humility. The very units we once trusted are themselves adrift on the same current that carries the stars. Out there, beyond the last quasar we have yet seen, more distant beacons wait, their light already on its way. Perhaps some of those photons left so early that they will bring us news from the dawn of the first black holes, the first galaxies, perhaps even the first stars. When they finally arrive, we will greet them with new instruments, new questions, and the same old wonder. And in that moment, the edge of the observable universe will quietly recede again, inviting us to sail a little farther into the dark. Imagine a beam of starlight gliding across the cosmos for 1 billion uneventful years. It threads the dark between galaxies, never touching a speck of matter, a perfect arrow of light. Then, a few million light years from Earth, it brushes the flank of a great cluster of galaxies. The cluster's gravity is invisible, yet it folds space like a soft blanket, and the beam, instead of sailing straight, arcs. It is not broken, not dimmed, only bent, gently, inexorably, until it arrives at our telescopes from two slightly different directions, forming twin images of the same distant star. One object now appears twice on the sky, and the space between those images is wider than the orbit of Neptune. No mirror is involved, no glass, no lens in any familiar sense. Only gravity, sculpting the geometry of distance itself. Einstein once scribbled the equations that foretold this quiet miracle. On paper, he watched starlight skirt the limb of the sun and calculated the angle of its deflection, less than the width of a coin held at arm's length. To measure such a slender deviation, astronomers would have to wait for a total eclipse, compare plates, and trust star positions measured during minutes of darkness. In 1919 they did, and the stars had shifted exactly as Einstein promised. A new kind of astronomy was born, not of bigger mirrors or darker skies, but of curved space-time. The act of seeing became the act of weighing. Out among the galaxies, the bending is no longer minute. There, clusters thousands of times heavier than the Milky Way gather dark matter like halos of smoke. Light that grazes them can be turned through tens of degrees, stretched into luminous arcs, or smeared into perfect Einstein rings. The same galaxy may appear in 5 separate places around the cluster, each image brighter than the original, magnified by the curvature. We call this strong lensing, and it is nature's own telescope, free of charge, millions of light years wide. Between the dramatic arcs lie subtler distortions. A faint background population of galaxies, billions of them, arrives with every square degree of sky, each one slightly squashed, slightly rotated. No single galaxy looks odd, but 10,000 together reveal a pattern, like ripples on a lake that betray the stones beneath. Weak lensing, we name it, and from its statistical whisper we reconstruct the dark scaffolding upon which the visible universe hangs. Weighing a cluster this way is like judging the depth of an ocean by watching the color of the sky reflected upon its waves. The bending encodes distance. The more space is curved, the larger the spread between the multiple images and the slower their light arrives. A single pulse from a quasar, split by a lens, reaches Earth again and again, each repetition delayed by days, months, sometimes years. We mark the intervals, count the seconds, and infer how far the quasar sits beyond the lens, how far the lens sits from us. We do this without needing to know how bright either object truly is. Geometry alone suffices. Thus gravity becomes a tape measure across the void, a ruler whose ticks are flashes of light separated by human heartbeats. Yet the ruler disagrees with other rulers. Measure the expansion of the universe with lensing delays, and the answer is one number. Measure it with infant relic light or with pulsating stars, and you receive another, close but stubbornly distinct. The mismatch is small, only a few percent, but the universe has no room for approximations. Somewhere in the curvature, or in the calibration of candles, or in the physics of the early cosmos, a secret waits. Each new lensed quasar tightens the error bars without yet settling the dispute. So we keep watching, keep timing, keep counting. Sometimes the delays themselves become the story. A supernova, exploding once in a distant galaxy, reappears in our monitors like a delayed echo. We mark the calendar, wait, and months later the same star blows up again on the opposite side of the cluster. Between the first flash and the last, a year may pass, and during that year the universe has expanded, stretching the very yardstick by which we measure it. By catching such reruns early, we can predict when and where the next image will brighten, then station telescopes around the planet ready. When the predicted date arrives and the star indeed ignites on cue, we feel the fabric of spacetime flex beneath our comprehension. All of this relies on the patience of photons. They do not protest when their paths are bent. They simply obey the curvature, arriving late but unaltered. We, the living, are the ones who must be patient, waiting decades for a single measurement to mature. In the meantime, new lenses are found by algorithms that sift sky surveys faster than any eye. Each discovery is a gift, a chance to weigh invisible matter, to refine the expansion rate, to glimpse galaxies too faint to be seen except through gravitational amplification. The universe, indifferent, keeps handing us lenses like someone scattering seeds across a field. There are limits to the gift. A lens perfectly aligned casts a ring, but misalignment leaves only broken arcs, and if the background source is too compact, the splintered images merge into an unresolved blur. Some lenses are shallow, their clusters too light, and the deflection is lost beneath the noise of atmospheric twinkling. Others are so massive that they focus the light into a tangled knot of caustics, a chaos of micro-images impossible to reconstruct. Behind every success story lie 100 ambiguous smudges, hints of bending that we cannot yet decipher. Still, the method matures. We have begun to map the dark matter within individual galaxies, tracing how it piles up in clumps 1,000 light-years wide. We watch galaxies distort as they drift through cluster centers, their shapes sheared like clouds in a crosswind, and from the shear we read the density of the invisible. We find that dark matter refuses to be smooth. It forms filaments and knots, a ghostly anatomy beneath the luminous skin of stars. By combining hundreds of lenses, we assemble a three-dimensional web, the scaffolding upon which galaxies later condense like dew upon a spider's thread. One day lensing will chart the expansion history of the universe image by image, epoch by epoch. We will watch the Hubble tension resolve itself or deepen, forcing us to revise our equations. We will track solitary black holes wandering through the halo of the Milky Way by the brief brightening they impose upon background stars. We will witness the first generation of galaxies, magnified by foreground protoclusters, their ultraviolet light stretched into infrared ribbons. Each observation is a small act of defiance against the darkness, a refusal to let distance remain unknowable. Until then, we sit quietly on our small planet, eyes pressed to the eyepiece of the cosmos. Between us and the edge of everything stand invisible masses, bending starlight into patterns that only patience can decode. We measure the delays, weigh the void, and feel the scale of the universe settle into our thoughts like dust on water. The light itself does not care that we are here, yet it carries the weight of galaxies to us, a courier that cannot be bribed, only redirected. In that redirection lies a truth both simple and immense. Space is not a box within which things move, but a participant, supple and responsive, holding the memory of every mass that has ever curved its fabric. And so, with each new arc and ring, we are reminded that distance is not merely a number to be read off a scale. It is a path that gravity can fold, a duration that expansion can stretch, a question that sometimes answers itself in duplicate images of a single star. We look, we wait, we measure again. Somewhere beyond the last lens, the first light ever emitted still travels, unimpeded, carrying forward the story of its birth. It may yet brush another cluster, bend once more, and arrive at a future eye, billions of years from now, bearing news of a universe we can only dimly guess. Imagine a single photon, born in the furnace of a star so far away its light has been traveling since before Earth had oceans. It leaves the star's surface, slips past the last cooling shell of hydrogen and steps into the dark. From here to its destination, us, lies nothing and everything. Nothing in the sense that no planet, no star, no galaxy interrupts the straightest line geometry allows. Everything because the emptiness itself is alive with whispers. Wisps of hydrogen colder than any Arctic night, threads of helium stretched into filaments millions of light years long. and a mist of ionized gas so thin that a terrestrial vacuum chamber feels crowded by comparison. This tenuous ocean is the intergalactic medium, and every photon must swim it. At first, the journey feels effortless. For 1,000,000 years, the photon sails through regions where atoms are spaced like scattered houses in desert country, one every few cubic meters. It brushes a hydrogen atom, exchanges no energy, continues. But gradually the density rises, not much, just enough that the photon begins to feel the gentlest tug of resonance. Hydrogen's lone electron vibrates at a precise frequency, a cosmic tuning fork. If the photon arrives carrying exactly that energy, it is swallowed, momentarily, then spat back out in a random direction. To our instruments, the photon has vanished. Its energy is absorbed, subtracted from the spectrum like a note lifted from a symphony. Multiply this by billions of clouds strung between us and the distant beacon, and the once smooth rainbow of light becomes a dark forest of missing lines. The Lyman Alpha Forest, we call it. Each trunk a hydrogen cloud at its own epoch, each gap a silent record of how long ago that cloud drifted in the way. Look at a spectrum and you are reading the itinerary of light. Here a cloud 4 billion years old, here another only 2. Here a filament so sparse it contains less mass than a handful of air yet stretches for 100 million light years. The lines bunch up the farther back you look, a crowd at the distant gate, telling us the early universe was smaller, denser, more cluttered. By measuring the spacing of these shadows, we weigh the void itself, counting protons and neutrons that refuse to glow in any other way. We are weighing the invisible, and the number surprises us. Half the ordinary matter we thought the universe should hold hides in these cobwebs. But hydrogen is only the beginning. Between the filaments lurk heavier elements brewed in ancient stars and blown out by supernovae. Carbon, oxygen, silicon, atoms that can clump into dust grains no larger than smoke particles. A photon meeting such a grain does not resonate. It is simply nudged again and again until its path wanders like a drunkard crossing a square. Some photons are scattered back into the dark, some are absorbed and re-emitted as heat. The farther they have to travel, the more grains they meet, so the distant universe appears not only fainter but redder, as if seen through a sky perpetually thick with sunset haze. Astronomers speak of attenuation curves, but the heart of the matter is simpler. Space itself has fog. Every galaxy we photograph is thus a little exaggerated in brightness, a little understated in distance, until we account for the dust we cannot see. And then there is the Great Cleansing. Earlier than 400 million years after the Big Bang, the gas between galaxies was not merely tenuous, it was opaque. Ultraviolet light could not travel more than a few thousand light years before being devoured by neutral hydrogen. Imagine standing inside a starlit room whose windows are painted over. The bulbs glow, but their light dies inches from the glass. So it was when the first massive stars ignited, pouring ultraviolet torrents into the surrounding dark. Photon by photon, they chipped away the neutrality, ionizing hydrogen into bare protons and free electrons. Once ionized, the gas no longer absorbed the same ultraviolet frequencies. The universe turned transparent. We call this epoch reionization, and its signature is written in the faint polarization of the cosmic microwave background, as delicate as breath on a mirror. Every photon that reaches us from beyond that era has passed through the frontier of this cosmic dawn, its original energy slightly sapped by the scattering of free electrons. We see the galaxies, but their colors are shifted, their brightness subtly demagnified, like coins at the bottom of a clear but moving stream. Correct for this, and the universe grows older. Ignore it, and distances shrink like a wool sweater in hot water. So the intergalactic medium is not a curtain pulled aside once and forgotten. It is a living lens, changing with cosmic time. When we measure the redshift of a supernova, we are not simply clocking the expansion of space. We are also reading how much gas the light has slogged through, how much dust has reddened it, how many electrons have nudged it off course. Subtract these effects, and sometimes the candle burns brighter than expected. The universe appears to accelerate faster, dark energy grows stronger. Add them back conservatively, and the acceleration relaxes, though it does not vanish. Thus, the tenuous fog between galaxies shapes our most existential numbers, the age of everything, the fate of everything. Consider the weight of that ignorance. We build instruments the size of city blocks to catch every stray photon, yet the calibrations hinge on gas so sparse that a comet's tail feels like a hurricane by comparison. We speak of precision cosmology, but precision is relative when your ruler is made of shadows and your mileposts are themselves drifting. Still, the wonder is that we can measure at all. Each absorption line is a fossil cloud, each attenuated galaxy a weather report from 10 billion years ago. The universe has not hidden its story, it has simply written it in vanishing ink. Pause for a moment and let the scale settle. A photon that left a galaxy when the universe was 1/10 its present age has, in Earth years, been traveling for 12 billion years. During that span, our planet formed, cooled, spawned microbes, dinosaurs, symphonies, and telescopes. Yet the photon's own diary of that odyssey is only a few pages long. A forest of lines here, a slight reddening there, a polarization twist at the end. All the rest, superclusters colliding, galaxies pinwheeling, stars being born and dying, is invisible to it and therefore to us. History is mostly blank space, with occasional footnotes scribbled by hydrogen. What remains when the photon finally arrives is a whisper of the original flame. Its energy is less, its direction minutely altered, its wavelength stretched by both the swelling of space and the scattering of matter. We collect it in a mirror, guide it through glass, register it as an electric pulse, and from that pulse reconstruct the distance to a place that may no longer exist. The uncertainty is not a failure of engineering. It is the signature of the journey itself. To measure the universe is to read a book whose pages have been rain-soaked, sun-bleached, and carried by winds. We can still discern the plot, but every chapter bears the creases of travel. And so we return to the quiet between the galaxies. It is easy to speak of emptiness, harder to feel its subtle resistance. The intergalactic medium is the breath of the cosmos, exhaled by ancient stars, stirred by dark matter's gravity, ionized by quasars, enriched by supernovae. It is the truest commons, belonging to no galaxy, claimed by no civilization. Every photon we see has been its guest, every spectrum its autobiography. We study it not because it is loud, but because it is the hush that shapes all cosmic music. In the end, distance is not a number but a story of encounters. A photon's flight is measured not merely in kilometers or light years, but in the clouds it avoided, the dust it grazed, the electrons that nudged it. We too are part of that story. Our eyes the final mirror, our minds the last lens. When we look out, we are reading the travel journal of light, knowing that the ink is fading, the pages are tearing, and the book itself is still being written. The next chapter waits beyond the reach of today's telescopes, where older photons, if they exist, have yet to arrive. Imagine for a moment you could stand still in space. Not on Earth, which refuses to keep still, but out in the black ocean between galaxies, where the nearest solid thing is 1,000,000 light years away. There, with no planet beneath your feet, you would discover something unsettling. The word distance is secretly the word time wearing a disguise. A light year is not a span you can pace across. It is the life story of a photon, 9 trillion kilometers folded into 12 quiet months. Pick any star you like. The light that touches your retina tonight left that star when your grandmother's grandmother was learning to walk. The star may have already died, yet its afterimage is still on its way, a telegram from a sender who no longer exists. Hold that paradox gently, because everything in deep space is both here and gone. Now suppose you stop being stationary. Suppose you build a craft that can cruise at 99% of light speed and you steer it toward that same star. Physics keeps its own ledger. In the ledger kept by people back home, your voyage will last 106 years. In the ledger you carry in your pocket, only 15 years will have passed. The distance between launchpad and destination has not changed for them. For you it has contracted to a thin ribbon you could almost leap across. Which length is real? Both. Neither. Distance, Einstein showed us, is a question of who is doing the measuring and with what clock. The light year is trustworthy only if we add a second clause, measured by whom at rest relative to what. This is why cosmologists speak of two kinds of distance. Proper distance. The reading you would get if you could freeze the expansion of the universe, lay out a cosmic tape measure, and breathe calmly while galaxies hold their pose. Comoving distance. The reading you accept when you allow the universe to keep breathing, when every point in space is drifting away from every other point like dots on the surface of an inflating balloon. The two numbers diverge like railway tracks heading into heat haze. 10 billion comoving light years translates to about 6 billion proper light years today, because the space between has been stretching while the light was in transit. The galaxy we record as 10 billion light years away sent its photons when it was only 6 billion light years distant. The photons traveled through a corridor that was itself elongating beneath them, a moving walkway that added kilometers faster than they could run. Hold that second paradox beside the first. Distance expands behind you while you are still walking toward it. Time dilation adds a third layer. Park a telescope on the rim of a black hole and another far from any gravity well. Let them both watch a supernova detonate halfway across the cosmos. The distant telescope sees the flare rise and fade in weeks. The telescope beside the black hole records the same spectacle as a slow-motion waltz lasting years. The difference is not in the star but in the slope of time where each watcher stands. A light year measured beside the compact star is longer than a light year measured out in the void, because the second hand of the clock refuses to tick at the same rate. Even on Earth we confirm this. GPS satellites orbit high enough that their clocks race ahead of the ones in our phones by a few billionths of a second each day. Multiply that drift across galactic epochs and the discrepancy becomes a canyon. So when we say the observable universe is 93 billion light years wide, we are summoning a number that already contains corrections for every stretching corridor, every sagging clock, every motion we could never personally witness. The statement sounds precise, yet it is stitched together from a patchwork of reference frames no human will ever occupy. We map the cosmos in the conditional mood. Consider a simple thought experiment. You and a friend synchronize perfect atomic clocks. Then one of you boards a ship that accelerates to within a whisker of light speed, coasts for 10 of her years, turns around and returns. When the hatch opens, she has aged 20 years. The friend who waited on Earth has aged many thousands. During the voyage, each traveler felt time flowing normally. Heartbeats, thoughts, and digital watches all seemed regular. Yet the reunion reveals a private chunk of duration that one carried in her bones, while the other watched civilizations rise and fall outside the porthole. Now replace the friend with a beam of light. A photon launched from a galaxy 13 billion light years away spends the trip riding a stopwatch that never advances. From its perspective, departure and arrival occur on the same instant. The gulf we measure in billions of years is, for light, a single, timeless now. Distance collapses to zero when time refuses to pass. Stand outside on any clear night and you can perform the experiment in reverse. The light entering your pupil has traveled for decades, centuries, millennia, yet it ends its journey in the transparent jelly of your eye. You become the arrival event for something that left its origin before you had a name. In that moment, you are both the destination and the afterlife of a particle that never aged. The paradox is no longer out there among the stars. It has crossed the threshold and come to rest inside you. We habitually think of space as a stage and time as the curtain that rises and falls, but the light year dissolves the boundary between backdrop and performance. Distance is the lag in the signal, and the lag is all we ever see. Even the sun you greet at dawn is the sun of 8 minutes ago. Hold your hand up to the warmth and you are shaking hands with a ghost that has not yet noticed if it still exists. Carry that realization to its limit and every map becomes a diary, every diary a funeral register. Yet the same intertwining grants us memory on the grandest scale. Because light takes time, the past is not lost. It is simply elsewhere, still traveling. An observer living 30,000 light-years toward the galactic center could, in principle, collect the photons that bounced off Earth when our ancestors painted cave walls at Lascaux. With a mirror large enough she could read the light, reconstruct the continents, the clouds, the pigments of bison rendered in ochre. History is not erased. It is scattered at large across the sky, a library whose books are bound in beams. Still, the universe keeps its own counsel. We will never catch those escaping pages and rewrite them. The speed of light is not an engineering hurdle. It is the tempo of causality itself, the rate at which the cosmos permits influence to travel. Outrun it and you would arrive before you departed, unraveling the sequence that allows questions to precede answers. Nature defends the order by refusing to let masses reach the speed of light. Acceleration thickens inertia until time itself folds backward and the equations collapse into contradiction. So we remain pilgrims on the slow side of the barrier, reading by afterglow. What then is a light year? It is a unit that forces humility into grammar. It is the distance at which space and time admit they are the same fabric, that a kilometer is a second wearing a disguise, that a year is 1,000,000,000,000 kilometers folded into heartbeat. It is the interval that guarantees every sky we gaze into is a museum, every glance an archaeology. It is also the interval that promises something else. Tomorrow's sky will be different. Wait 1,000,000 years and some of the stars you loved will have stepped beyond the horizon of the observable. Their light will have been stretched by expansion into infrared fog, then into microwave whisper, then into silence. Other stars, newly formed, will step into view, carrying fresh letters from farther shores. The vault above us is a shoreline that erodes and rebuilds while we watch, a tide made of distance and duration. Hold these threads together. Distance shrinks at high speed, time dilates in gravity, space itself stretches beneath the traveler, and every measurement depends on the stillness of the measurer. The light year is not a fixed rod. It is a sentence spoken in the language of relativity, a sentence whose meaning changes with the accent of the speaker. Yet it is the only language we share with the galaxies. We cannot step outside the universe to obtain a final, neutral answer. We stand inside the story, using words that are themselves part of the plot. Perhaps that is why the night sky evokes such wordless awe. It is not merely beauty. It is a mirror that returns our own reflection stretched across impossible span. We reach for the stars and discover we are reaching backward through our own duration, touching a past that includes every generation that ever lifted its eyes. The light year breaks our habitual sense of scale, but it also stitches us into something larger, a continuum where space is time made visible and time is space waiting to be traveled. In the hush between heartbeats, remember this. Every mile is also a minute, every second a silent mile. The cosmos does not distinguish. Only we draw the line, and even the line is moving, stretching, aging, forgetting. We live inside a story whose pages are written in distance and read in time. A story whose next chapter begins the instant we lift our gaze and decide, once again, to look. Astronomy has always been the art of measuring the unmeasurable. Tonight, we stand at the edge of a new catalog of tricks, listening for echoes so soft they could be the footfalls of galaxies. The old yardsticks, parallax, Cepheids, the gentle dimming of a distant bulb, have carried us millions of light years, yet the mirror they hold up is still clouded by a few percent of doubt. A few percent sounds small, until you realize that, at the horizon of the visible, those percentage points translate into hundreds of millions of years of cosmic history misplaced. So we are sending quieter rulers into darker valleys. The first is already overhead. Gaia, the wide-eyed sentinel parked at the Sun-Earth Lagrange point, is not a telescope in the romantic sense, no golden mirror cupping starlight like a trembling hand. It is a spinning pair of eyes that repeatedly scans the entire sky, measuring angles to the width of a human hair seen from the moon. Each star's shift, as Earth moves from one side of its orbit to the other, is a tiny heartbeat. Gaia listens to 1 billion such heartbeats, then plots the pulse rates on a three-dimensional map. With every year of data, the map grows muscles. With every new release, the errors shrink like drying paint. Already, we have seen individual stars in nearby galaxies whose distances are known to within 1 part in 1,000. An accuracy our grandparents reserved for the nearest handful of suns. When the mission ends, its legacy will not be a photograph but a living lattice, a reference grid against which every future telescope will calibrate its gaze. Yet even Gaia has a horizon. Beyond a few million light years, parallax fades into noise. To press farther, we must abandon the idea of a single eye and build, instead, a synthetic skull. Space-based interferometry is that skull. 2 or more telescopes separated by hundreds of meters in the vacuum of space. Their light combined with lasers so stable they would notice the width of a single atom over the distance from London to Paris. The pair acts like a lens as wide as the gap between them, turning starlight into moire patterns whose fringes encode angles smaller than the event horizon of a stellar black hole. The concept is old on Earth. Radio astronomers have linked dishes across continents, but optical light demands a precision that air corrupts with every passing breeze. In orbit, the silence is perfect. A future constellation of free-flying mirrors will drift in formation, breathing against solar pressure, constantly adjusting their separations to within a few nanometers. From their combined whisper, we will read the parallax of Cepheids in galaxies 50 million light-years away, tightening the cosmic ladder until the lowest rung almost touches the highest, removing the knots where error once hid. But angles are only half the story. Nature has begun to hand us clocks whose ticks are explosions of pure geometry. When 2 neutron stars spiral together, they tear the fabric of spacetime, sending out a tsunami of gravitational waves. The shape of that wave carries, encoded within it, the intrinsic loudness of the crash. Detect the wave, measure its pitch and volume, and you know how bright the event was. Compare that to the apparent brightness your telescope's record, and distance falls out like solving for the far side of a triangle. Astronomers call these signals standard sirens, because they wail across the universe tuned by Einstein's equations alone, unblemished by the dust and chemical vagaries that trouble ordinary candles. We have heard only a handful so far, yet already they nudge the Hubble constant toward a value independent of cosmic ladders. In the coming decade, ground-based observatories will be joined by a detector so large its arms will span millions of kilometers in space. Every year it will record hundreds of neutron star duets, each a fresh measurement of cosmic expansion. The statistics will grow until, perhaps, the dispute over how fast the universe expands collapses into a single quiet number. Meanwhile, another form of ranging is rehearsing within our own planetary backyard. A laser pulse leaves an observatory in New Mexico, strikes a mirror left on the moon by Apollo astronauts, and returns 2.5 seconds older. That round trip, repeated for 50 years, has told us the moon is retreating from Earth at the speed a fingernail grows. Now imagine swapping the moon for a spacecraft coasting beyond Pluto, its mirror a wafer of polished sapphire cooled to near absolute zero. Each photon must leave Earth perfectly timed, cross the gulf, and find a target only centimeters wide. The Echo, when it comes, has traversed more than 10 billion kilometers. From the delay, we will triangulate the craft's orbit around the Sun with a precision of meters, turning the outer solar system into a sounding board for gravity itself. Over decades, the cumulative record will betray the gentle tug of unknown masses, perhaps a faint perturbation from a true ninth planet, perhaps a residual pull from the curvature of spacetime predicted by theories beyond Newton. Laser ranging thus becomes both tape measure and seismograph, sensing distance and the invisible hand that alters it. And still we crave a messenger that flies without mirror or reflector, a particle that can cross a galaxy as easily as moonlight crosses a window pane. Neutrinos are that messenger. Born in the hearts of stars, in the violent swirl around black holes, or in the self-immolation of a distant supernova, they carry news of cataclysms otherwise hidden behind curtains of dust. Because they rarely interact, they arrive unscathed, preserving both energy and arrival time. A burst of neutrinos from a supernova in the Large Magellanic Cloud reached Earth 3 hours before the first photon, a harbinger racing ahead of the collapsing shock. When the next star blows in a galaxy beyond our own, a lattice of detectors buried under Antarctic ice or nestled in the Mediterranean abyss will record the flood. The brightness in neutrinos, set against the brightness in light, will give a distance immune to dust and to the uncertainties that beset optical candles. In principle, a single supernova seen in both neutrinos and photons could calibrate distances across 20 million light-years. In practice, we wait for the universe to oblige us with such a show, and for our detectors to grow large enough to catch the faintest sprinkle. Each of these futures is fragile. Interferometers must keep mirrors aligned to the radius of an atom, while the solar wind tugs like a mischievous child. Gravitational wave observatories must distinguish a cosmic vibration from the pull of ocean tides on the far side of the planet. Neutrino telescopes must sort a dozen star-borne particles from the cosmic ray debris that continually rains like confetti. Yet history favors the patient. The same species that once measured Jupiter's moons with a handheld glass now proposes to unfold kilometer-wide diffraction gratings in space, letting starlight spill across them like water across silk, reading the spectrum of a galaxy whose photons left before Earth had trees. What will we do with such knowledge? Measure again the age when expansion began, perhaps discover that darkness splits into two darks, one older, one younger. Map the flow of galaxies so completely that we see the faint scar left by a sister universe that brushed against our own before the first stars flared. Or simply rest, knowing the ladder no longer wobbles, that each rung is pinned to the one below with the certainty of iron. But certainty has its own horizon. Every refined distance pushes the mystery one step farther back, into whatever lies beyond the observable, into whatever medium carries the galaxies like scattered seeds on an invisible tide. We measure to belong, and we belong to something still becoming. Tomorrow's instruments will not end the questions. They will only teach us to ask them with a quieter voice, the way a child learns to whisper when entering a cathedral. Out beyond the last mirror, the dark is already folding the next surprise. We will need new languages of ripples, of ghostly particles, of light held in perfect stillness. And when those languages finally answer us, we may find that distance itself was never the thing we sought, only the silence between heartbeats, a silence in which the universe, for a moment, remembers we were here. A single light year is not a span of time, it is a span of distance, nearly 6 trillion miles of it, yet the phrase itself slips through the mind as if it were a gentle lyric. 6 trillion. The tongue forms the words with ease. The mind, however, staggers, then quietly gives up. Somewhere between the first trillion and the second, the machinery designed for tracking antelope and gathering fruit declares the number unreal and files it away under miscellaneous. This surrender is not a personal failing. It is an ancient adaptation. Our ancestors never needed to tally beyond the seasons or the herd, so the brain specialized in the middle scale, minutes, meadows, handshakes, while the cosmos specialized in everything larger. When children first hear that the nearest star lies 400 million kilometers away, they often picture a very long road lined with familiar kilometer stones, each one dutifully counted by an imaginary traveler who never sleeps. By the time the class reaches lunch, the child has quietly abandoned the image, sensing that the traveler would have died of old age long before leaving the solar system. The adult version of the same error is more subtle. We replace the traveler with a fast spaceship, swap kilometers for light years, and tell ourselves we have grasped infinity because we have exchanged one unit for another. Yet the underlying short circuit remains. We are still trying to line up cosmic distance like fence posts, counting one after another until comprehension appears. The universe declines to cooperate. Its scale is not linear. It is exponential, and exponentials do not march, they bloom. To feel the bloom, begin with something your body already knows. Hold your hands a meter apart. Between them, right now, fits 1 billion atoms laid edge to edge. A meter is handy, human, domestic. Now multiply by 1,000, you have a kilometer, a pleasant walk. Multiply again by 1,000, you have a megameter 3 times through Earth itself. Again by 1,000. You reach gigameters, the realm of moons. Once more and you are counting in terameters, the province of planets. Each step costs you 3 zeros but costs the imagination a cliff. After only 7 such cliffs you have outrun light itself for a year, yet you have used up only a casual sentence of arithmetic. The mind, lacking any sensory anchor, detaches from the numbers and floats free, like a balloon snipped from its string. Strangely, this floating carries its own kind of comfort. Neurologists who monitor volunteers in planetariums find that when scales sprint beyond everyday experience, the parietal lobes, those meticulous bookkeepers of space, quiet down. Activity drifts forward to regions that knit memory and emotion. The subject stops calculating and starts feeling. Heart rate drops, pupils widen. A soft vertigo arrives, interpreted by most watchers as awe. Awe is not a decorative flourish added to make science palatable. It is the cognitive signature of a brain that has recognized its map is too small and has chosen, wisely, to relinquish the compass. Societies have long anticipated this surrender and prepared stories to cushion it. Nordic sailors spoke of a sky bridge made from the glowing footprints of gods. Aboriginal Australians sang of an emu in the dark between the stars, her body outlining the dusty lane we now call the Milky Way. Each metaphor translated the inconceivable into the intimate, not to reduce it, but to grant the listener a place to stand while gazing outward. Cultures are patient teachers. They know that if a child can feel the emu, someday the same child may be willing to learn the physics of spiral arms. Today the metaphors arrive through different conduits. Planetarium software can wrap the night sky around a living room like a blanket. Virtual reality headsets let a user walk the 43-meter span that separates our sun from its nearest neighbor, if the sun were shrunk to the size of a grapefruit. The journey ends in 3 casual steps. Yet the software insists those steps represent 4 light years, and the brain, fooled by the body's motion, stores the ratio as lived experience. Teachers report that students who make the virtual walk retain the scale longer than students who merely see the numbers. Muscle memory, it seems, is more trustworthy than numerical memory, even when the muscles are imaginary. Still, every tool hits a ceiling. You can simulate a galaxy cluster, but you cannot simulate the billion-year patience required for light to cross it. The mismatch between what we can show and what there is to know renews itself with each zoom of the cosmic lens. Psychologists call this the magnitude problem. The larger the phenomenon, the smaller the fraction any mind can hold at once. Mathematicians cope by compressing complexity into symbols. Poets cope by compressing symbols into images. The rest of us cope by oscillating between the two strategies, alternating equations with metaphors the way a climber alternates hands on a cliff face, each hold too small to rest on forever. Perhaps the most honest adaptation is simply to notice the oscillation and call it home. When the Voyager spacecraft looked back from beyond Neptune and snapped the famous pale dot photograph, Earth appeared as a fuzzy pixel suspended in a sunbeam. Astronomers reminded us that every cathedral, every concerto, every kiss occurred on that dot. The image worked because it did not ask us to count kilometers, it asked us to switch contexts. The brain cannot contain 6 trillion miles, but it can contain the memory of every childhood summer, and both contents fit within the same pixel. By toggling between the vast and the cherished, we glimpse the architecture of existence without needing to master its blueprint. There is humility in this toggling, and humility is not the same as defeat. The recognition of a limit can be the beginning of a relationship. Lovers do not understand every neuron in one another's minds, yet they learn to trust the mystery. In a similar way, acknowledging that a light year will never feel concrete allows us to treat distance as a companion rather than a puzzle to be solved. We can measure it precisely, travel it if engineering ever permits, without demanding that it shrink to human size. The cosmos remains vast, we remain small, a conversation becomes possible. Where does the conversation go next? Outward, inevitably. Having admitted the inadequacy of perception, we are free to refine the instruments that extend it. Telescopes larger than cities will soon collect photons that left their stars before Earth had trees. Data banks will swell with starlight that no living organism will ever touch, yet algorithms will map and color until patterns emerge. Each pattern will invite new names, new stories, new metaphors, because the brain will still be human, still hungry for narrative. The task is not to outgrow the hunger but to keep feeding it with ever stranger meals. And when those meals no longer fit on any plate we recognize, something curious happens. The universe begins to feel less like an expanse and more like a duration. A light year is distance only in the sense that a year is time. Both are conversions of one currency into another, space into time, time into memory. Stand under a clear sky long enough and you may sense the conversion happening. The Pleiades you see is the Pleiades of your grandparents' childhoods. The light left the cluster back when radio was young. You do not perceive a place so much as a moment held in transit, a cosmic photograph still developing. Distance dissolves into delay and delay into biography. This is why, when people are asked to describe their first encounter with astronomical numbers, they often answer with a story. The night they drove away from city lights, the moment they first saw Andromeda floating like a smear of cold milk, the sudden awareness that the photons ending on their retinas began their journey when saber-toothed cats still roamed. Numbers are forgotten, the visceral timestamp remains. The brain, thwarted by magnitude, records duration instead, and duration is something it understands because it is made of it. Every heartbeat is a small credential. So we inherit a paradox worth keeping close. To know the universe is to admit the impossibility of knowing it, and yet the admission itself becomes a form of acquaintance. We navigate by admitting we are lost, measure by confessing our rulers are short, see by acknowledging our blindness. A light year stays ungraspable, but something else is grasped: a poise, a willingness to remain mid-sentence, an appreciation for questions that outlive the asker. Somewhere beyond the last charted galaxy, a photon begins a journey that will never intersect Earth. No eye will ever catch it, no mirror will ever redirect it. Its path is valid nonetheless, and the fact that we can speak of it, that we can frame its absence in language, suggests a kinship between mind and cosmos that distance cannot erode. The brain may break against the scale, yet the crack lets in light, and the light travels, year after year after year. Imagine a child on a beach at dusk. She holds a flashlight toward the sky, clicks it on, and swings the beam across the clouds. In that instant, she is convinced she has touched the moon. Years later, she learns that her beam is still traveling, that it has slipped past the planets and is now gliding through the dark between stars. By the time she is gray-haired, the light she sent out will have gone less than 1/30th of the way to the nearest sun. The child becomes the grown author who writes a novel in which starships cross such abysses in weeks. The same person, two versions of distance, the felt and the measured. Science fiction lives in the tension between them. Writers need the story to move, so they fold space, they warp time, they let captains punch a big silver button and arrive. Yet the reader, somewhere inside, remembers the beach, remembers that light is patient. This quiet memory is what gives the best tailies their ache. When a character stands on the deck of a ship that has left Earth at 99% of the speed of light, she may return home to find that her friends have died of old age while she was gone a season. The numbers are hidden in the background, but the emotion is the sound of surf, steady, familiar, and impossible to argue away. Travel time versus relativistic effects is not a classroom problem here. It is the difference between saying goodbye and being the one who is still waving when the harbor is empty. To build a universe that feels wide, an author must first decide how wide is too wide. If every voyage takes lifetimes, empires cannot meet, lovers cannot quarrel across starfields, news cannot outrun decay. So distances are shrunk, not by decree but by device. An Aldous drive, a Banks hypersphere, a wormhole bored like a moth hole through linen. Still, the writer who respects the meter of light years keeps a second map folded in a pocket. On that map, Proxima is still 4.2 away, and the Pleiades still 444. The reader senses the hidden scale and feels the cold outside the hull even while the cabin is warm with voices. This is world building with realistic distances. The stage is vast, yet the actors are close enough to speak if the script allows them to age at different rates. Such stagecraft invites a familiar ghost. Where is everyone? If the galaxy is roomy enough for 1,000,000 fiction franchise civilizations, why does the real night remain polite, silent, almost quaint? The Fermi paradox haunts the novelist as surely as it haunts the radio astronomer. Every imagined federation is a reply to the hush, a wish scribbled in the margin of an empty ledger. The silence becomes a character, the long pause in which a pilot wonders whether the voyage is pilgrimage or exile. Isolation is not merely terrain. It is the villain that needs no costume, the cold that seeps through plot armor. When the last outpost stops hearing from Earth, the reader confronts the same loneliness that the scientist faces while staring at equations that say we ought to have neighbors yet yield none. Often the most extravagant inventions are tethered to the most pedestrian facts. Herbig Harrow objects, those glowing jets young stars fire into the dark became, in Le Guin's prose, the birth wind that carries ships. Pulsars, once nicknamed LGMs for little green men, still tick like lighthouses in Niven's stories, though now we know they are only spinning embers. Real astronomy donates the grain of sand around which the pearl is grown. A ring of gas circling a black hole is renamed the River of Night, but its orbital velocity remains what the physicist calculated. The writer's gift is to let the reader feel the heat of that disk, while never showing the tensor calculus that keeps it from flying apart. Inspirations from real astronomy are the scent of pine that drifts through a cabin. The story happens indoors, yet the forest is always present. Balancing drama with scientific fidelity is less a formula than a negotiation carried out night after night at the desk. Add too much accuracy and the pages freeze. Add too little and they float away like untethered balloons. The secret is to keep cause and effect married even when the setting is polygamous. If a journey to Deneb takes a decade in ship time but a century at home, then the farewell letter must still arrive after the coffin. Obey that rule and the reader will follow you through a wormhole. Break it without noticing and the reader closes the book, suddenly reminded that stars are too far apart for coincidence to be kind. The best authors keep a small, honest ledger. One column for wonder, one column for watts per square meter, the two totaling something that feels like truth. Yet even the most disciplined tale leaves a seam where the real leaks through. Close the novel and you are back on the porch, aware that no engine hums beneath the floorboards, that the constellations overhead are arranged not by narrative need but by the drift of spiral arms. The night does not care whether your story required a twin of Earth. Still, something has changed. The sky feels less like a ceiling and more like a page that has not yet been written upon. You measure your life again in birthdays, in paydays, in the time it takes kettles to boil, and you recognize these units as provincial, charming, and irreplaceable. The distance that breaks our brains has also broken open a small, necessary space in the heart. Room for patience, room for the long view. So we stand, as always, between two editions of the same atlas. One is printed in fibers of light, the other in the chemistry of ink and hope. Each needs the other to be legible. Without the stories, we would not endure the intervals. Without the intervals, the stories would have nowhere to travel. Somewhere, a probe crawls outward at 0.1% of the speed of light, a toy boat on a Pacific of night. It carries plaques, pictures, greetings. The authors who invented faster ways will never shake its hand, and the child on the beach will be dust long before the craft passes the first frost line of comets. Still, the gesture matters. It is our signature on a contract written in slow photons. We were here, we knew the distances were lethal, and we tried anyway. The next chapter waits quietly like a star that has not yet risen. Light years have carried us far beyond the familiar. From the moon's silver arc to the silent shores of galaxies billions of years away, we have used distance as our measuring rod, our compass, our clock. Yet every ruler, however long, eventually meets a surface it cannot span. Out here, where photons grow tired and the fabric of space itself seems to exhale, distance stops answering questions and begins asking them. Imagine standing on the summit of a dark island. The ocean around you is expanding, not as water does, but as a living parchment stretched by invisible hands. Ripples from the horizon reach your feet, but they arrive distorted, weakened, no longer sure of the shape that made them. We call one of those distortions dark energy. We do not know its nature, only its signature. Every cubic meter of space gains a whisper of new room each instant, so gentle that a trillion cubic meters would not nudge a grain of sand. Accumulated across the gulf between galaxy clusters, the whisper becomes a shout. Galaxies already separated by 10 million light-years drift apart faster every day, like polite strangers who begin to step backward the moment they notice one another. Measure the expansion, and you find the universe ballooning as if some vast lung inhales forever. Name the lung, and you have named our ignorance. Distance once felt solid. A star 10 light-years away seemed simply 10 years of travel time for light. But if the space beneath that light is stretching, the miles themselves are growing while the photon crosses them. The star may be 11, 12, 13 light-years away by the time its image arrives. So every measurement of cosmic distance carries a hidden clause, assuming the ruler does not lengthen while you read it. Dark energy makes the clause impossible to ignore. It forces us to admit that the most basic question, how far is that, has no fixed answer across deep time. We can chart the rate of swelling, yet we cannot say what stores the pressure. A new kind of field. The relic of a quantum ripple frozen into space. Or perhaps a ghost of Einstein's greatest blunder, resurrected and smiling. Whatever it is, it writes itself into every remote mile, and every mile refuses to translate its handwriting. The clash appears the moment we try to calibrate the expansion itself. Measure the retreat of galaxies with exploding stars, and you obtain one speed for the cosmic heartbeat. Read the afterglow of the Big Bang, the gentle microwaves that still reign on every square centimeter of sky, and you obtain another. The two differ by a few kilometers per second per megaparsec, less than a walking pace across a distance so vast that light needs 100 million human lifetimes to cross it. Yet the mismatch is stubborn, persistent, announced by independent teams on opposite hemispheres using opposite techniques. It is like hearing two drummers inside the same parade, each convinced the tempo is sacred. Somewhere, a hidden downbeat is being counted twice, or not at all. The trouble may lie in our understanding of distance itself. Perhaps supernovae are not as standard as we believe. Perhaps the early universe hit a brief, early burst of expansion that still echoes in the numbers. Or perhaps, strangest of all, the speed of light, our tireless yardstick, has stories it never told us. Until the tension dissolves, every cosmic mile is ringed with parentheses of doubt. Move inward from the cosmic edge to the quiet suburbs of galaxies, and distance plays a subtler trick. Here stars are scarce. The bright posters of gas and dust have thinned to a mist. Yet something holds the outermost hydrogen clouds in orbit, something that bends their trajectories as if an invisible Catherine wheel were turning in the dark. We map the motion, calculate the gravity required, and find 5 times more mass than we can see. Dark matter. It forms a halo whose outer boundary no telescope has yet confirmed. Push far enough and the orbital speed should drop, the way outer planets in our solar system slow beneath the sun's weakened grasp. Instead, the speeds stay high, suggesting halos that extend like ghostly continents well past the visible stars. How far does the halo stretch? 1,000,000 light-years? 10 million? Does it fray into filaments or end in a sudden cliff? Every answer rewrites the mass we must place in the dark, and every new mass changes the geometry of space itself. So the question of distance, where does a galaxy end, blurs into the question of substance. What is the stuff we walk through but never touch? Now zoom out even farther, past clusters, past voids, past the subtle drift of one side of the sky away from the other. Some versions of inflation, the burst that ignited cosmic expansion, predict that beyond our horizon the same process repeats, not once but endlessly. Each region would have its own Big Bang, its own age, perhaps its own slower or faster light. In such a multiverse, distance becomes not a span but a boundary of possibility. Travel far enough and you would not merely reach a new place, you would reach a new set of physical constants. What looks like a measurement error here might be an accurate reading of conditions over there. Distance, then, is the sieve through which reality sorts its variations. Yet by definition, these regions are forever beyond our sight, separated from us by space swelling faster than light can run. We cannot point to them on a map, only infer them from the math that otherwise refuses to add up. They exist in the same way the far side of a rainbow exists, undeniable, unreachable, painted only by inference and vanishing when you step too close. Even on the threshold of the knowable, distance informs the fundamentals. Why is gravity so weak? Perhaps because most of its strength leaks into extra-spatial dimensions rolled smaller than an atom. Test the idea, and you need distances so tiny that you must bounce particles within fractions of a proton's girth. Here the energy required climbs beyond any earthly collider. So we turn back to the cosmos, where nature itself provides the extremes. Watch two galaxies collide and the shockwave races through their dark halos. Measure how long the ripples take and you constrain the width of any hidden dimensions. Distance becomes the particle physicist's caliper, the only one large enough to grip a force we feel as weight yet cannot explain. Pause and listen to the quiet between these questions. They are not failures of science. They are its outer membrane, the place where knowledge meets the not yet known. Every civilization that has measured land, ocean, or sky has eventually encountered a horizon. The horizon is not the edge of the world, it is the edge of the eye. We extend it with mirrors and antennas, with mathematics and imagination, yet it continues to retreat, carrying new archipelagos of mystery just out of reach. What lies there will demand new conceptions of distance, perhaps new conceptions of number itself. Until then, we keep the tally in light years, even while suspecting that the final answers will require a unit we have not yet named. We began by trusting distance, letting it guide us outward like lanterns held along a mountain path. Step by step, the lanterns revealed chasms we did not suspect, and the chasms revealed that the path itself is moving beneath our feet. Now we stand at the last visible marker. Beyond, the night is uncharted. We carry forward only questions, carried gently, like embers cupped against the wind. Somewhere ahead, the next lantern waits to be lit. A beam of light leaves a star and travels for 100 years before it brushes your retina. In that instant, you do not simply see the star, you witness the past wearing the costume of the present. The gap between the pulse and your eye is called a light year, yet the true distance is vaster than numbers can carry. It is a corridor of silence, a museum of frozen moments, a reminder that every celestial postcard arrives late and still asks to be read. Stand at the shoreline of any ocean at dusk and look toward the horizon. The rim of water is only a few miles away, already farther than an unaided voice can travel. Beyond that, another horizon and another until the curve of Earth hides them. Now let the mind keep walking. Across the Atlantic, across the stratosphere, past the moon's chalky cliffs, past the sun's furnace, past the outer gates of the planetary frontier, the scale inflates like lungs filling with air. Each step outward multiplies the quiet. Eventually, the silence becomes so wide that even light, the fastest emissary we know, needs decades to cross a single room of darkness. At that threshold, distance stops behaving like distance and becomes duration. Space becomes time. Time becomes memory. And memory becomes the only map we own. We are, each of us, standing on a pebble that has already completed its billionth circuit around a modest star. The pebble is wet with oceans and wrapped in a thin, breathing film. From the edge of the galaxy, the whole drama of empires and heartbreaks, of symphonies and vaccines, is less than a flicker on a pale blue dot. The knowledge should humble us, yet it also stitches us into the fabric of something immense. For if the universe can be proud of anything, it can be proud of producing creatures small enough to tremble and curious enough to measure their own smallness. Light years teach humility, but they also teach continuity. Every photon that lands on a child's outstretched palm began its journey before that child's grandparents were born. The photon carries in its wavelength the temperature of the surface that launched it, the chemical mood of the star, the faint flavor of interstellar dust it picked up along the way. It is a letter mailed by matter and received by flesh. In this sense, the past is not behind us. It rains on our upturned faces at every moment. We inhabit a present that is perpetually seeded by antiquity. Likewise, the light that departs Earth today will travel outward for centuries, perhaps to glance off the mirror of some distant telescope operated by descendants we will never meet. Our present becomes their past, their future becomes our legacy. The transaction is slow, but it is faithful. Nothing is lost except the illusion of isolation. There is comfort in such continuity, yet also responsibility. If our world is rare, then its rivers and coral reefs, its libraries and lullabies, are rarer still. We may someday find other living spheres, but none will carry the exact chorus of sparrows at dawn or the precise smell of rain on hot pavement. The distances that protect the cosmos from casual traffic also protect its local miracles from replacement. Damage done here cannot be patched by spare parts shipped from Alpha Centauri. A light year is a moat, Earth is the castle inside. The siege engines are ignorance and neglect. The defenders are patience, imagination, and the stubborn insistence that knowledge is worth the effort of maintenance. Curiosity is the one cargo we can launch that weighs nothing and still arrives. It travels at the speed of thought, slower than light yet able to leap across centuries in a single generation. When Aristarchus proposed that Earth circles the Sun, his voice could not cross the Aegean in time to outrun skepticism, but his idea eventually orbited the planet 1,000 times. When Henrietta Swan Leavitt measured the pulses of Cepheid variables, she could not vote in her own country, yet her ruler stretched across megaparsecs. When a child today builds a cardboard solar viewer, she stands at the far end of an unbroken relay of questions that began before writing. Each investigator passes a candle forward through the dark, trusting that someone farther along the path will shield the flame from the wind of indifference. We measure the unknown because we are measured by it. A light year is not merely a unit. It is a mirror. In its face we see how briefly we live, how thinly our atmosphere clings to us, how readily our machines stall in the vacuum. Yet the same mirror shows that we are capable of picturing what we will never touch. We name the gaps between galaxies, calculate the weight of a star, predict the collision of neutron stars, and then sit back to hear the chirp of gravitational waves exactly on schedule. The universe is vast, but not vast enough to swallow every trace of understanding. A part of it, however small, can be folded into the wrinkles of a brain. The folding takes effort, and the effort takes generations, but the crease, once made, cannot be erased. Some nights the sky feels like an ocean overhead, and we are shipwrecked sailors clinging to a raft of atmosphere. Other nights it feels like a cathedral whose ceiling is so high that echoes return as hymns. Both metaphors are true. The distance that breaks our brains also mends them by offering a canvas larger than our quarrels. From the vantage of a light year, national borders vanish, stock markets flatten to noise, and yesterday's outrage is indistinguishable from static. What remains visible is the long glow of cooperation. Radio dishes arrayed like henge stones on desert plains, telescopes stacked like organ pipes on a cold mountain, data cables slung beneath oceans so that knowledge can outrun the rotation of Earth. These collaborations are slow, often maddeningly so, yet they are the only way we have found to keep company with something bigger than ourselves. Perhaps the most secret gift of the light year is that it teaches deferred gratification on a cosmic scale. A star may burn for 10 billion years, quietly fusing hydrogen into helium, not because it has a goal but because gravity allows no haste. We, who fret if a web page loads in more than a second, learn from that patience. To measure a galaxy, we must be willing to wait for multiple rotations of Earth around the Sun, to calibrate instruments, to recalibrate them again, to argue over decimal points in journals, and then to hand the unfinished chart to students who will argue over finer decimals. The payoff is not fame. The payoff is participation in a story whose ending will be written in a language we will not speak. The light year reminds us that some answers arrive after the questioner is gone, and that this is not failure but fulfillment of a contract signed by mortality itself. So when you next look up and see the soft, steady glow of Vega, remember that the photons were emitted when humanity was still perfecting the bicycle. They have been racing through the dark for 25 years merely to touch your cornea and vanish. Their journey is over. Yours continues. You are the forward edge of light that has not yet been emitted, the still unwritten chapter in a book whose pages are scattered across parsecs. The distances that separate star from star are not voids to be feared, but pages to be turned slowly, with reverence, by hands that know the weight of turning. And somewhere ahead, farther than we can count but not farther than we can imagine, waits a boundary we have not yet named. It is not the edge of the universe, for the universe has no edge but the edge of our current sight. Beyond it lie more galaxies, more histories, more children building cardboard viewers under alien suns. We will reach them only in light, never in body, yet the reaching matters. Every measurement is a handshake across the dark. Every image is a postcard that says, "We were here, we saw, we wondered." The postage is paid in patience. The return address is a planet small enough to fit inside a single heartbeat. The cosmos whispers that humility and grandeur are roommates in the human heart. A light year is the corridor they share. Walk it gently, and the echo of your footsteps will sound like tomorrow asking to be borrowed.